On behalf of National Institute of Technology Warangal and Department of Mechanical Engineering, I extend a warm welcome to all of you to the inaugural session of 5-day GIAN workshop on physics-based data-driven modeling in additive manufacturing and sustainable manufacturing technologies such as additive, coating, subtractive, and hybrid. We are privileged to have distinguished guests, faculty members, and participants with us today. May I now invite our esteemed dignitaries to kindly join us on the dais? Please, sir. Please join me in welcoming our beloved director, Professor Vidyadhar Subudhi. So, we wish to inform you that our esteemed director, Professor Vidyadhar Subudhi, is unable to join us in person due to some busy schedule. However, he will be joining us virtually to address and engage with us during the program. So, we'll welcome Director in Charge, Professor Ratish. Distinguished expert and project collaborator, Professor Panwisawas. Distinguished expert and project collaborator, Professor Joshi. Distinguished expert and project collaborator, Professor Joshi. Director in Charge, Professor Ratish, sir. Dean of International Relations and Alumni Affairs, Professor S. Srinivas Rao. Head of Department of Mechanical Engineering and Workshop Coordinator, Professor Y. Ravi Kumar. Co-coordinators of today's workshop, Professor A. Venugopal. Co-coordinators of today's workshop, Professor. We will begin our program with a national song. I request everyone to kindly stand.
Vande Mataram, Vande Mataram, Sujalam Sukhalam, Malayaj Sheetalam, Sasya Shyamalam Mataram, Vande Mataram, Shubhra Jyotsna Pulakitayamini, Pullakusumita Drumadala Shobhini, Suhasini Sumadhura Bhashini, Sukhadam Varadam Mataram, Vande Mataram, Vande Mataram.
Please be seated. Thank you. As we begin this significant occasion, let us illuminate our path with light of knowledge and wisdom. I humbly request all the dignitaries to kindly join us for the Jyoti Prajwalan.
असतो मा
and the workshop on physics-based and data-driven modeling in additive manufacturing. Please, sir.
Respected Director in Charge, Professor Ratish Kumar, and two distinguished international experts. One is Professor Chenapat from Queen Mary University of London, and other one is Professor Srikant Joshi from University West, Sweden. Professor S. Srinivasarao, Dean, IRAA, and GIAN Local Coordinator, Professor Venugopal, my senior colleague, my dear participants, students, and my dear colleagues. A warm welcome to you all for the inaugural function. So I am delighted to stand before you that we are going to organize two GIAN courses. So the first one is on physics-based and data-driven modeling in additive manufacturing, and other one is sustainable manufacturing technologies, organized by the Department of Mechanical Engineering. And it's my privilege to introduce Mechanical Engineering Department. The Department of Mechanical Engineering exists right from the inception of the institute, that is 1959. The department presently offers one undergraduate program in BTech in Mechanical Engineering with an intake of 165 students. And the department offers 5 MTech programs in various specializations, namely thermal engineering, manufacturing engineering, computer integrated manufacturing engineering, machine design, and automobile engineering. The department is also offering doctoral degrees in various fields of mechanical engineering. Presently, the department has 90 full-time and 40 part-time scholars on rolls. At present, the department has 50 regular faculty with research experience in various specializations in mechanical, and the academic labs are equipped with good experimental facilities like 6-axis milling machine, IR camera, machine, 3D printing, friction and wear tester, air jet erosion, wheel alignment, vehicle onboard diagnostic, to name a few. Department has liaison with reputed industries and R&D organizations such as NFTDC, DMRL, DRDL, RCI, ASL, ARCI, BHEL, GTRE, ADA, and more. The department has acquired a funding about 5.5 crores through external funding projects from DST, SCRB, DRDO, and so on. And the department also has Center of Sustainable Energy Studies, Hexagon Capacity Center as a Center of Excellences, and also department associated with Center of Excellence for Digital Manufacturing and Automation. Pleasure to talk. One of the GIAN is physics-based and data-driven modeling in additive manufacturing. So we have 60 participants. So out of 60, 36 are students, that is PhD scholars 32, PG students 3, UG students 1, faculty 19, industry and scientists 5. And among 36 and around 18, 19 participants are registered for the credits. And coming to the participating institutions, so we have 8 IITs. One is IIT Madras, IIT Kharagpur, IIT Roorkee, BHU Varanasi, IIT Jodhpur, IIT Ropar, IIT Jammu, and IIT Tirupati. And we have 3 participating NITs, NIT Trichy, NIT Nagaland, and NIT Warangal. and other institutions like VIT Vellore, PSG Coimbatore, Anna University, Amrita, and so on. And we have participation from NITTTR Chandigarh, RR CAT Indore, GMRL Hyderabad. And coming to additive manufacturing and NIT Warangal, so we have a close association. So we at NIT Warangal took the initiation first time in India to start a PG program with the specialization MTech in additive manufacturing in collaboration with Central Manufacturing Technology Institute, CMTA Bangalore. We launched this program from academic year 2014-15. And if you see the global, so it was valued 15.10 billion US dollar in 2021 and is projected to grow 18.33 billion US dollars in 2022 to 83.90 billion US dollars by 2029. So which we can see the cumulative annual growth rate is 24.3% during this forecasted period. So rapid increasing digitalization, increasing adoption of advanced technologies like Industry 4, smart factories, robotics, machine learning, and other fuel the demand for the online additive manufacturing or 3D printing for simulation purpose. And this course is very well connected to the simulation. And if you see the applications like aerospace companies, so they are using this technology to manufacture various hardware parts. For instance, Boeing leveraging industrial 3D printing to manufacture the interior parts of the plane, and NASA using to build the rocket engines and parts of the satellites. Automobile industry expecting to show a huge adoption of this technology. Rapid tooling incorporate with additive manufacturing has become the priority of many automobile manufacturers. Customization of automotive interior is another major application of technology in automobile industry. So one of the biggest obstacles has been cost, but now the companies like MakerBot, Ultimaker printers, now you can buy at around 2000 USD, that is 1.2 lakhs Indian rupees. Roughly it is the equivalent amount of a basic Apple iMac computer. So coming to the deliberations during these 5 days, so we have planned 10 theory sessions, each of 1.5 hours, that is total 15 hours, and which is going to cover fundamentals of mechanistic modeling, modeling and simulation of laser powered by additive manufacturing for microstructure and mechanical properties, thermomechanical modeling of additive manufacturing for calculating residual stresses and distortion, fundamentals of data-driven modeling and its application in AM, multi-scale, multi-physics modeling of heterogeneous non-equilibrium microstructures in metal AM, design for additive manufacturing and basics of machine learning, and finally integration of physics-informed machine learning and data twins to additive manufacturing. So these are the theory sessions. And coming to the lab sessions, so we have around 7 labs, and which is catering to prediction of composition changes by machine learning techniques using open source software, design for additive manufacturing, generating lattice structures, simulation for defect reduction and microstructural prediction using ANSYS software, build setup preparation for metal additive manufacturing using 3D expert software, working on metal additive manufacturing machine, and post-processing techniques for metal additively manufactured parts. And coming to the examination, who opted for credits, maybe around 18, 19, I need to check, maybe 18, 19 or register for the credits that we are going to earn, and we are going to conduct a test. On the hands-on practices, the 50% weightage will be given to the evaluation process, and 50 marks quiz at the last day. And you are going to earn 2 credits. Why? Because it is 29 lectures has been going to deliberate here. So with this, thank you for the opportunity given.
Thank you so much, sir, for shedding light on departmental activities and vision, and also for the insightful overview of the workshop. Now I invite Professor A. Venugopal to give an overview of the workshop on sustainable manufacturing technologies. Please, sir.
Good morning, one and all. The distinguished guests, the international experts for both the GIAN programs, Dr. Panwisawas for the course on physics-based and data-driven modeling in additive manufacturing, and Professor Joshi for the course on sustainable manufacturing technologies, including additive, coating, subtractive, and hybrid. Our beloved director, Professor Bijadar Subudhi, who will be joining online, and Professor Ratish Kumar, who is the in-charge director, acting director for today, and Dean Interracial Relations and Alumni Affairs, Professor Srinivas Rao, Head of the Department, Mechanical Engineering, and also the coordinator of one of the GIAN courses, Professor Vairav Kumar. My colleague, Dr. Manjiya, another coordinator along with me for the second GIAN program. Participants from various engineering colleges, faculty, and students. It gives me a great pleasure to welcome you all for the GIAN course on sustainable manufacturing technologies, additive, coating, subtractive, and hybrid. In fact, manufacturing has always been a keystone of progress, driving technological advancements and economic growth across the globe. The traditional methods of manufacturing often involve high energy consumption and significant material waste. However, as we navigate these challenges of the 21st century, climate change, resource depletion, and global population growth, it has become clear that the development of sustainable manufacturing methods is necessary. Of course, we all know that sustainable manufacturing aims to create products through processes that reduce environmental impact, conserve resources, and promote economic and social sustainability throughout a product's life cycle, from design to disposal. This 5-day course offers hands-on knowledge in 2 advanced areas of sustainable manufacturing, that is additive manufacturing and surface engineering. Of course, we all are aware that additive manufacturing builds components layer by layer from digital models, enabling complex, lightweight, and material efficient designs. AM reduces waste, shortens production time, allows easy customization, and minimize emissions by enhancing material and energy efficiency. Surface engineering modifies material surfaces to improve properties like hardness, wear and corrosion resistance, and thermal stability. Advanced coating techniques extend product life, increase efficiency, and reduce environmental impact, lowering resource consumption by minimizing replacements. This course covers principles and applications of AM and surface engineering with insights into integrating these with traditional manufacturing. Participants will explore case studies and real-world applications aligning with India's Make in India and Skill India initiatives. The interdisciplinary nature of this course reflects the complexity of sustainable manufacturing. It requires expertise in material science, engineering, design, and process optimization, coupled with a strong commitment to protect the environment. We are privileged to have the leading experts, both from academia and industry, Professor Joshi from the University of West, Sweden, the international expert, and also we are going to have 2 more experts from industry, from India, Mrs. Dr. Deepa Srinivasan, who had a vast experience working in GE and Pratt & Whitney, and now she is also associated with one of the private engineering colleges in Bangalore, Ramaya Institute of Technology. And Dr. Santosh Nagaraj, who is working in Hexagon. They'll be sharing their knowledge and experiences with us during these 5 days of the course. Through interactive lectures, practical demonstrations, and collaborative discussions, this course will provide a robust platform for learning, innovation, and networking. Before we proceed further, I would like to express our heartfelt gratitude to the management of all the academic institutions for sponsoring their faculty and students to attend this GIAN workshop. In fact, the participants' composition is like this. We have about 13 faculty members joining from various parts of this country. PhD and PG students about 20, and undergraduate students about 10. We hope the insights and skills gained during this workshop will enrich not only your individual journeys, but also contribute to the progress of your institutions and the broader academic community. Once again, thank you for your invaluable support and participation. Let us make this workshop a productive and impactful experience for everyone. Thank you.
Thank you, sir, for such a thorough and comprehensive overview. I would like to invite Professor M. Manjaya to introduce our distinguished international expert and project collaborator, Professor Chinnapat Panwisawas from Queen Mary University of London.
Thank you. It's my pleasure to invite the guest on the foreign expert for this one of the GIAN program, Dr. Chinnapat Panwisawas. He is currently an associate professor in the Materials and Solid Mechanics department, and as well as a deputy director of graduate studies, and as well as director for the Material Science and Engineering program at School of Engineering and at the Queen's Mary University of London. And he joined this Queen's Mary of London in 2022 July, and he obtained his PhD degree from Metallurgy and Materials Engineering from the University of Birmingham in 2013, and he got his the BSc degree in the first honors in the physics department from the Choklong University of Thailand in 2008. After conferment of his PhD, he joined a partnership of the Research Simulation Manufacturing Materials Research Group at Rolls-Royce and University of Technological Center at the University of Birmingham from 2013 to 2018. And in the year of 2018 June, he was awarded EPRS Ukeri and as well as Innovation Fellowship to conduct his research project, and as a principal investigator on additive manufacturing materials, and as well as a senior fellow in the EPSRC Innovation Fellowship at the Department of Materials from the University of Oxford in the London. And before joining to Queen's Mary University of London, he was an associate professor in the digital manufacturing, associate director of NASCO UK Research Center, and as well as innovation fellow at the School of Engineering, University of Leicester. And with this, he has vast experience in investment casting, and as well as laser and electron fusion bed welding, as well as additive manufacturing, and he has more thorough on the numerical modeling of additive manufacturing aspect. His main research interest focusing on the multi-scale materials modeling of liquid and solid interactions, particularly aim of high performance alloys using the integrated computational engineering materials ICME approach. And as well as Dr. Panwisawas holds his visiting professorship at Chulalongkorn University at Thailand, and as well as Shimane University in Japan, and as well as Shanghai Jiaho Tonggo University at the China. And also he is a visiting academician at the University of Oxford and as well as University of California, USA. With this brief introduction, I will welcome to deliver the over the inaugural session. Thank you, sir.
Thank you, sir, for the kind introduction. Please join me welcoming Professor Chinnapat Panwisawas to address the gathering. Please.
Thank you very much, Professor, for the kind introduction. And I mean, first of all, I would like to thank Director, Deans, and the Head of Mechanical Engineering for the invitation, and also all the very good hospitality that I received this day. So I'm very honored to be here to talk you something about my experience in the fundamental of modeling of additive manufacturing. And I believe this will be a good step forward for us for the further collaboration in research and also education in the years to come. So thank you very much for organizing this and your hospitality. Thank you.
Thank you so much, sir. I would like to invite Professor M. Manjaya to introduce our distinguished international expert and project collaborator, Professor Shrikant Joshi from University West, Sweden.
Once again, I am warm welcome to all of you, and it's my pleasure to introduce the guest and as well as the international expert, Professor Shrikant Joshi. He is one of the GIAN program foreign expert in sustainability additive manufacturing process, hybrid and subtractive, and as well as hybrid manufacturing process. And Professor Joshi is an accomplished chemical engineer with over 3 decades of experience in the academia and as well as industry. He currently serves as a professor in the Department of Engineering Science at University West, Sweden. And Dr. Joshi obtained his PhD in the chemical engineering from University of Idaho in 1987 and MS from the Research Polytechnic Institute in 1983, and BTech gold medalist from Usmania University in 1982. And Dr. Joshi professional journey spans several leaderships and research roles. Since 2015, he has been working as a professor at University of West, contributing significantly to the research in surface engineering and material sciences. And prior to this, he held a roles of International Advanced Research Center for Power Metallurgy and as well as New Materials, that is at ARC in Hyderabad, as Associate Director, including the Additional Director from 2013 to 2015, and as well as Associate Director from 2005 to 2013. Additionally, he serves as a Dean at University of Hyderabad School of Engineering, Science and Technology from 2008 to 2009. And also prior to that, he was working as a scientist as DMRL almost 15 years before joining to ARCI. And he is an expert in the additive manufacturing, thermal spray coatings, and laser surface engineering, and also is working in the area of electron beam processes. And Dr. Joshi research interest mainly lie in the intersection of the advanced manufacturing material sciences. He had led numerous high impact research projects such as advanced coatings for the enhanced sustainability project funded by the KK Stephen in 2023, and Green Bat project on solid state lithium batteries funded by the Vinova in 2022. His work also extends the coating for the solid state thin film batteries under the Novel CABS projects in 2021, and high performance coatings for the industrial applications and Ipraco Coat project in 2019. And Dr. Joshi's experts has been recognized through the various prestigious awards. In 2023, he was inducted into a Hall of Fame by the ASM Thermal Spray Society, and he holds a fellowship with the notable organizations including the Institute of Materials, Minerals and Mining IOM3 UK, and also as well as ASM International. His accolades includes the Metallurgist of the Year Award from India Ministry of Steels in 2009, and Vaishak Research Award in Material Science and Technology in 2011. Dr. Joshi has contributed extensively to academic literature. Over the 200 peer-reviewed journals he has published, and 12 book chapters he has published, and 4 books he has edited in surface engineering and thermal spray coating technologies. And he holds 8 patents, and also he filed 6 more patents. He is undergoing the innovation in the contribution of the materials engineering aspects. He remains as actively involved professional societies including ASM International, Metal Research Society of India, and the Institute of Indian Metals. With this brief introduction, I welcome you, sir.
Thank you, sir, for the kind introduction. Please join me welcoming Professor Shrikant Joshi to share his insights with the gathering.
Good morning, everyone. I'm going to be speaking for the next 5 days, so I won't take too much time this morning. But for me, it's a great pleasure to be here for several reasons. First is I'm coming on this beautiful campus after 15 years almost, and it's lovely to see the changes that have happened. On a more personal note, I'm very delighted also to be here because as additional director of ARCI, I wanted to put in place some mechanism for our senior research fellows to pursue higher degrees while they were working with us at ARCI. And as part of that, this institute was the first one with which we established a joint PhD program. And I recall seeing Professor Venugopal and signing an MOU with this institute in that capacity. So it's a great pleasure to see that that program still continues. If I remember, me and Professor Venugopal had the first joint PhD student as a part of that program. Of course, I left before the guy finished, but it's good to see that that program continues. Coming back to additive manufacturing and particularly surface engineering, it has been my first love. I must say second, otherwise my wife will be upset. Yeah. It's been my second love, and it's a little bit complicated, as I was telling both Dr. Manja and Professor Venugopal, to run a course like this because on both of these subjects, we run a course that runs the entire semester, right? So to pack this both into 5 days and then deal with bachelor students, postgraduates and faculty in the same course. Yeah, it's a little bit tough. But I want the engagement to continue beyond these 5 days, right? And I'm also hopeful that being here today will perhaps get started a three-way collaboration involving your university as well. I'm really looking forward to that. So thank you very much. I will see more of you in the next 5 days, of course. Thank you.
Thank you so much, sir. We will now hear a few words from Professor S. Srinivasrao, Dean of International Relations and Alumni Affairs.
Good morning to all. Respected Director of NIT Warangal, Professor Vidyadhar Subodhi, he is joining through online, and Professor Ratish Kumar, in charge Director, and respected foreign faculty, Dr. Chinnapat Panwisawas and Professor Shrikant Joshi, and coordinators of these two 5-day faculty development GIAN courses, Y. Ravi Kumar and A. Venugopal, and another co-coordinator Manjaya, and all the faculty members of Department of Mechanical Engineering, and the participants who came from different parts of the country for attending this 5-day GIAN course. So good morning and welcome to all of you once again. So these 5-day GIAN courses, or two courses are starting today. All of you know that one is physics-based and data-driven modeling and additive manufacturing, and sustainable manufacturing technologies, additive, coating, subtractive and hybrid. So one course is on additive manufacturing, other course is on additive and subtractive manufacturing technologies. So by attending these courses, all of you will be getting exposed to the latest technologies in additive manufacturing. So I thank these faculty members for initiating for writing a proposal for this GIAN program and contacting the foreign faculty members, and they have shown a lot of interest, and finally Government of India has approved, and by crossing all these process and all this course was approved, and we are very happy to see foreign faculty members here, and their interaction will be definitely useful for all of us for developing the research advancements and technological developments in the area of additive manufacturing as well as additive and subtractive manufacturing technologies. So myself, I am S. Srinivasrao, Professor in Department of Electrical Engineering. I am holding an additional charge of Dean International Relations and Alumni Affairs for the tenure of 2 years duration, started from this year, July 1st. So this Dean Office, Dean International Relations and Alumni Affairs Office is coordinating different programs sponsored by Government of India, and also the collaboration made by various faculty members with foreign universities and institutions for technological advancements and increasing research potential at NIT Warangal for the benefit of faculty members as well as students who are studying in these institutions. And at the same time, by this type of programs, we are calling the faculty members from different parts of the country, so that all will be getting exposed to the latest technologies by listening to the foreign professors. So along with this GIAN course, this Dean International, this office will look after the another programs, that is Spark Scheme for Promotion of Academic and Research Collaboration, UK India Foundation and Research Initiative, Heritage Program, BRICS, DAD and MITAX, etc. These type of sponsored programs are also handled by this office, along with the alumni relations. And this GIAN course, about GIAN course, Government of India in 2015 has initiated this global initiative for academic networking in higher education, aimed at tapping the talent pool of scientists and entrepreneurs internationally to encourage their engagement with the Institute of Higher Education in India, to enhance the technical collaboration for the benefit of the society as a whole. These programs are not only confined to the one country or one region or one area. These research areas are identified, and these programs are conducted for the benefit of the whole world. Till now, this is the GIAN Phase 4 program is running. Under this program, these two are the first courses started in this year, this Phase 4. And previously, we have successfully completed the GIAN 3 phases. In 2015-16, 27 courses were conducted under GIAN Phase 4 with a sanctioned budget of 1.87 crores. In 2017-18, 41 courses were approved and conducted for an allotted fund of 2.48 crores. In 2019-13, 21 courses were approved under Phase 3 with a financial assistance of 1.41 crores. In this 2014-15, we have got 20 courses for an amount of 1.45 crores. In this series of this Phase 4 program, these are the course first or second, which course we may call as the first or second. These two courses are starting in the Phase 4. So I thank all the participants for showing interest to come physically and attend this program, and I thank once again the foreign experts for coming physically to interact with our faculty members, research scholars and institutions. This interaction will definitely useful for us to develop a collaborative research. So I wish all the best for these two programs, and once again I thank the coordinators for conducting this inaugural program of these courses combinedly. Thank you one and all.
Thank you so much, sir, for the valuable insights and encouragement. I now request our in-charge director, Professor Ratish, sir, to address the gathering.
Okay, so good morning to you all, and welcome to this wonderful two GIAN programs. Dignitaries on the dais, Professor Chinnapat and Professor Srikant Joshi. Professor Chinnapat from Queen Mary University of London, and Professor Srikant Joshi from University West. I'll call it as University West at Sweden, rather. And then dignitaries, Professor Srinivas Rao, the Dean IRA, and the director, both the coordinators of two GIAN programs together. In fact, Professor Venugopal, Professor Ravi Kumar, and Professor Manjaya, so who are organizing two GIAN programs together. And then participants, faculty, participants, and students, etc., student friends. So welcome to you all to this 246-acre, I should say, green sprawling campus spread into two phases, in fact, north and south campus in this institute. And this institute, for the information of everybody, is established in 1959. In fact, with one of the mechanical engineering is one of the branches which was there right from the inception of this institute in 1959, along with civil as well as electrical engineering. And we have grown strength to strength, of course, in the past 1.5 years with the leadership and stewardship of our beloved director, Professor Subudhi. In fact, there's a lot of changes which have taken place in terms of, as Professor Srikant Joshi is mentioning, there's a lot of change in the campus, sir. We have seen the green luster, and then a lot of infrastructure have been added. And then there's a lot of, progress in terms of, research and development, in terms of publications, in terms of patents, in terms of technology transfer, in terms of overall, there is a very broad outlook changes have taken place in the last 1.5 years. In fact, under the able guidance and leadership of our beloved director, Professor Subudhi. Of course, coming to these two programs, I'm not an expert in this area, but I work in the area of civil engineering. I'm a civil engineering professor, basically. I'm also the Dean Planning and Development in this institute. I only say that, one of the topics is related to physics. I think physics-based data-driven modeling in additive manufacturing, right? So I think this is something like, something like for 3D printing, which we do normally in civil engineering, as part of civil engineering part is concerned. Additive manufacturing is something like 3D printing also, in fact. I mean, we do 3D printing of concrete and mortars. That means your, the cement, fine aggregate, etc. Maybe concrete, cement, fine aggregate, and coarse aggregate. And I think that's similar to this because you work in the area of metals, and maybe the same approaches related to the, the physical models and maybe data-driven approaches, including your machine learning, etc., might be is a part of this to probably improve the efficiency of this 3D printing process in manufacturing for better prediction of material behavior, etc. Maybe the precision is one more very important part. I think it also involves, as I understand, the real-time optimization part might be there for the manufacturing process, leading to better precision, faster production, and more reliable outcomes in the additive manufacturing applications. I think this should be the nutshell of what you are basically doing as far as the first course is concerned. Now, as far as the second course is concerned, it's more like, the sustainability related. And as Sir was telling that, this is a second love, additive manufacturing is second love. In fact, there's a beautiful love triangle between what we normally call it as strength, durability, and sustainability. So I think you are touching upon the third aspects, in fact, without compromising on the performance in terms of strength as well as durability. I mean, that's a common ground between all the different branches. I think the focus will be more on reducing the material waste and implementing energy efficiency. I think the words like adding means adding layer by layer as we do in 3D printing, and basically for minimizing the waste, while subtraction probably means your something like removing the material from a solid block or something like that, offering precision, right? And then coating, as I understand, is something like what we normally understand is in terms of improving the properties like corrosion or wear resistance, or improving the durability aspects, and probably I mean to say the surface properties. And hybrid techniques probably will include everything, like optimizing the sustainability, addition, coating, as well as subtraction, everything. So this is what I basically understand from this, and I really see that there are two great experts, one from Queen Mary University, London, as well as the other from University West at Sweden. I request both these experts also to spend some time going around the campus, and also, if possible, we can try to go for a sort of memorandum of understanding between these three universities, India, Sweden, as well as London, all the three universities. And I also request the participants to have a good time in the campus, and then don't just only concentrate. I mean, of course, it's a captive audience. When you say NIT Warangal, it's a captive audience. But at the same time, please try to explore, try to meet all the professors who are there in the department, because everybody is a gem in this in the Department of Mechanical Engineering, so they have their own expertise. I request that the participants who are coming from different parts of the country to please interact, and then probably you can try to make up your research collaborations, or maybe some students are there who can actually join in PhD courses, etc. And probably also when you go back, you see all the campus, the planning, etc. We have done a beautiful infrastructure has come and is coming. In fact, we are doing with something like a 450 crores of work we are doing with a lot of things which are coming up in terms of the lecture hall complex, residential quarters, and then we have a 2,500 seated amphitheater. So several things are basically coming up on the campus. So I wish you will have a pleasant time in this campus, and then when you go back, please take all the good things and then speak good about NIT Warangal when you go back. So thank you very much. Thank you.
Thank you so much, sir, for the valuable guidance and interaction. I request our beloved director, Professor Vidyadhar Subudhi, to address the gathering. Thank you so much, sir, for your inspiring leadership and vision for NIT Warangal. We are humbled that in spite of your busy schedule and commitment, you have made it to the point to interact with the audience. We now move to releasing the course material. I request the dignitaries to kindly join us for making this occasion. Thank you, everyone. A heartfelt thank you to all the speakers, dignitaries, and participants for joining us today. I now invite Professor M. Manjaya to deliver the vote of thanks.
Good morning once again all. It's my privilege to deliver the vote of thanks for these two GIAN programs. First and foremost, I extend my heartfelt gratitude and esteemed international experts, Professor Joshi and as well as Professor Panwisawas, for gracing this occasion with their presence and sharing their valuable insights over the programs. Your contributions have set to an inspiring tone for the program and emphasizing the critical importance of sustainable practices in manufacturing technologies and as well as numerical modeling in the additive manufacturing aspects. A special note to appreciation goes to our Professor Vidyadhar Subodhi, our respected director, for their unwavering support and encouragement which has been instrumental in making this event reality. And I also wish to express my sincere thanks to our the in-charge director, Professor Ratish, for his presence and gracing this occasion. And I also would like to thank our Dean International Relationship and Alumni Associations, Professor Srinivas Rao, for his continuous consistent guidance and as well as support in facilitating the GIAN program submission and ensuring successful organizing of this event. And also I would like to thank our gratitude on the extended initiation of the GIAN initiation from the Ministry of Education and as well as the IIT Hyderabad nodal coordinators for providing us with this robust platform for necessary and resources to conducting these organization programs and enabling us to engage with cutting edge research in additive manufacturing and sustainable technologies and all. Finally, I would like to acknowledge the tireless effort given by this organizing committee and also including the head of the department, Professor Ravi Kumar, and registrars and as well as the deans and faculty members, administrative staffs and as well as the volunteers who work for this program and all. Your dedications and the meticulations, the planning have been pivotal to the smooth execution of this event. To all the participants for your presence and the enthusiasm are making us the program like this meaningful. We look forward to your active involvement in these sessions ahead, which is for the 5 days, and hope this program enriches your knowledge and the perspectives. Once again, I thank everyone making this inaugural program grand success. Let us embark this journey of learning the same zeal with the commitment. Thank you once again all. Thank you.
Thank you, sir, for the kind words and expressing gratitude on behalf of all of us. Let us conclude this session with the national anthem. I request you all to please rise.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमालय हिमाचल यमुना गंगा उच्चल जलधितरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे.
Thank you so much. Before we proceed for the high tea, I request all the dignitaries and faculty members and participants to kindly join us for a group photo.
Yeah, please settle fast. We are already running late by 15-20 minutes. Yeah, we'll kickstart our sessions with today, and all our sessions will happen in this hall. So from now onwards, I'll request all the members of this particular GIAN course to come directly to this as per the schedule that is already announced. And coming to the lecture course, we are going to give you the QR code from which you can download all the soft material. Probably at the end of the lecture, we will display that. Okay. So now I request Professor Joshi to start our sessions. Thank you, sir.
Excellent. Good morning, everyone. Am I audible? Am I audible to everyone? Excellent. So, welcome to this 5-day course on what you see on the board. Yeah, sustainable manufacturing technologies. We'll talk mostly about additive and about coatings. Yeah, and of course there are ways to combine both, which then becomes hybrid. Yeah, and we'll also have some talk on subtractive. But that's what we are trying to avoid, right, when you do additive. But there is some merit in hybridizing that way as well. I just now heard that some people are still on the way. Their trains are delayed or some such thing. Yeah. But we will start in any case, right? And I want this to be different from a normal course, correct? It is very rare that I stay on a campus for 5 days. I have never done that in my life in the last 15, 20 years. Yeah, it's great. and all of you also are staying on campus, right? So feel free. I will in a minute put up my email ID, take my email ID and say, okay, I want to meet you at 6 o'clock today, and then we will try and meet, right? If you have any questions. Because it's very hard to do a course where there are BTech students, masters and PhD students and faculty, right? So there is a risk that whatever I say make some people unhappy, correct? You may say, oh, this is too high funda or this is too low funda or whatever, right? So I will try and correct that by meeting with you wherever I can, and then my ambition also is that I manage to be a resource for you. Later on, if you find something that you would like to know, you should just send me an email, even if I'm not here. If some of you PhD students are looking for samples, I hope I can send you some samples. Not everyone, and not all kinds of samples, but some. If I can support at least one or two of you, I'll be very happy. With some faculty, I will be delighted if I'm able to set up some sort of a collaboration. So I have an ambition which is larger than just a 5-day course, right? I want this to sustain. But first, let's talk about the course, how we are going to do this, right? So the main course faculty are the three of us here, right? So I will do most of the talking, unfortunately for you. But both Dr. Venugopal and Dr. Manjia will help with some courses. And I'm extremely delighted that we have been able to convince Deepa, who I've known for a long time. And this was intentionally done. We wanted to give you some industrial perspective, not just academic guys talking for 5 days, right? That's boring. So we wanted to give you an industrial perspective, and that's why I think we couldn't find two better people than these here. Deepa has a long background from GE R&D, from Pratt & Whitney after that, and her move to Ramaya is only recent, but she's mainly an industry person, not an academic. And Santosh, I've never met Santosh, but I've heard good things about him. He's from Hexagon, and I think he's a valuable addition to the kind of coverage we want in this course. Okay? So that's my email ID. If you want to set up, so take that down, use it in the next 5 days, use it beyond this course, but yeah, just feel free. That's what is important. Let's see how the schedule looks like. I'm a little bit confused here by this schedule. I wasn't aware of the inaugural, but we will find a way. I was going to talk a little bit about a short introduction. Fortunately, it's short, so I'll make up time there. Yeah, talk about introduction to sustainable manufacturing, and then directly get into metal AM. What processes are available. But Dr. Manjia, we largely stick to this, right? Yeah. So if I have time up to 1:15, I should finish these two. Is that correct? Yeah. Okay. Right. Then that is day one. First of all, some of you may be very disappointed that the other course has a book, and what the hell, you guys have not given us anything, right? But the title is Sustainable Manufacturing. So we want to be sustainable, right? We don't want to print books. Yeah. So as Dr. Venugopal said, you will get a QR code. There's everything there. Even what you don't want to see is also there. Yeah. So there's plenty of stuff there. Don't worry about that. So day two tomorrow, we will talk a little bit about feedstock for metal AM. And then we will have Dr. Manjia speak about sustainability in producing some of this feedstock powders. And yeah. And then later tomorrow afternoon, I'm going to talk about a very important aspect related to AM, which is post-treatment. Yeah. Why do we do post-treatment? How do we do post-treatment? What is the motivation for that?
let's talk about that. Day 3, so let me show this. Yeah, this is better. So day 3, it's a pleasure to have Professor Venugopal start off, right? And then that's when I begin to speak a little bit about surface engineering. So the way I will cover it is standalone. Yeah, I'm not going to at this point begin to combine surface engineering with AM, but I'll talk about surface engineering in general. An important part of this course is also the lab sessions in the afternoon. You will have it on most days, maybe not all days. For example, today you don't have a lab session, but on most other days you will have something happening in the lab. On day 4, we will wrap up with surface engineering. Surface engineering is such a vast field, right? Just like AM is, and it's older, so it's become even bigger. So there is a limit to what can be covered. But I hope I give you a good idea that as a designer, what a wide toolbox you have when it comes to surface engineering, what many different things you can do, right? And then we talk about design for AM. Santosh will do that, and then also an important related aspect is numerical simulation. Dr. Manja will cover that. And day 5 is when Deepa comes in and talks about 2 very important aspects. One is industrial qualification. Sometimes industrial qualification is very challenging, right? You build a part, but to actually use it, you need qualification, especially in key sectors like gas turbine, whether you're talking about aero engine gas turbine or even land-based. You need qualification. And then Deepa has some experience with that. And the other aspect is repair, right? That is a key anchor in sustainability, to reuse or remanufacture parts, right? So we thought that too is important, right? And some little bit of hybrid I'm going to postpone till this part, right? So I'll talk about AM separately, surface engineering separately, but talk about combining these 2 here, because I think that is where the future research focus can be, especially for the faculty who are out there. I think that's a good area in which you can pitch your grant applications and ask for money, right? So we will postpone it until that time, right? So busy 5 days, but as I said, if it goes too fast or too slow, just stop me and catch me at other times perhaps. What I have done is I have taken the liberty wherever possible to seek out expertise that is available around me, right? So if you take something like sustainability, it's a fairly new field. People have different imagination of sustainability. It means different things to different guys, right? So I have taken help from my colleague, Klaus Fredrickson, who is part-time at our university. He's part-time at Cambridge, and he also works a little bit on making a software that gives you data related to sustainability and that kind of stuff, right? So this to me is a very fuzzy field, right? Just to get to know you guys better, how many of you are BTech students here? Yeah, BTech students. How many of you are PGs here? And how many of you are faculty? Some faculty. Okay. So let's start with BTech. Yeah, any one of you BTech students, right? What is your understanding of sustainability? What is sustainability for you? Any one BTech student? Way of living. Very good. Yeah. We will lose too much time to ask others if they agree with you or not. But all right, way of living. Nice. Postgraduate guys out there, PGs, you are thinking of sustainability? Any one opinion? Come on, you guys have said, so pressure is on you. Yeah? Excellent. That's also good. Yeah? And faculty, then. Way of living, attending to our own needs without kind of taking over needs of the future generations. That's also nice. Faculty, anyone? Even more pressure. We have UGs who have answered, PGs who have answered, now faculty.
Processing of the raw materials to create the products by keeping environment in the priority.
Excellent, right? So we have 3 points of view. As we go along, we will see if any of them is correct, all of them are correct, or whatever, right? But thanks for your input. So here is a definition of sustainability from the UN. Meeting the needs of the present without compromising the ability of future generations to meet their own needs. Good job. So PG is winning so far. Yeah. So that's the definition from the UN, right? Seems simple and seems very close to what she said, but I'm not sure if she understood everything she said. Yeah, because this is a very deep statement in one sense, right? It's easy to write, but to actually practice or implement is very tough, right? And we will, in this short introduction, we'll try and get there eventually, right? So where is the starting point, right? So this is the definition, same thing that I showed you just now, which dates back to 1987. Oops, my thing is going different, right? So the starting point is here, yeah? This is okay to say, but how do you accomplish that, right? Because if we look around ourselves, it's a very complex ecosystem, correct? We have the planet and something that you said comes into play there. Yeah, how do you get raw materials or make products without harming the environment, right? You know, people, and both of you kind of spoke about people, and then there is business, correct? Which at least till recently had a single-minded focus. They wanted to make money, correct? They still want to make money, correct? So this is very, very complicated. How do you find some region like this, which takes care of everybody's ambitions, right? And still ensures that whatever we do is sustainable, correct? So that is what we are going to talk about. Not so much, but just to set the stage for, it's important for everyone to know. So this is now almost a mandatory course in our undergraduate program also on sustainability, just so that people have heard of it, right? Whether you practice practice it or not is little bit up to you, but I think everyone should practice it, correct? So you need to, whenever you're talking about sustainability, you inevitably need to take care of all three. You have to take care of the natural capital, you have to take care of the human or social capital. You must worry about ensuring that industries also survive, right? They can't take care of both of these and incur a loss, right? Then we are in deep trouble, correct? So all these three need to happen, and that is where we have a challenge. Why is that a challenge? What do these arrows mean? I mean, I must admit that this picture is from the internet, of course, Google Maharaj, yeah. But what do these arrows mean to you? They mean something to me. What do they mean to you? To me, they mean that all these three things are pulling in different directions, right? So there is pressure in entirely different directions when you talk about planet or humans as a race, and their ambitions and the desire for the industry to make profit. All of them pull in different directions, and that's where it becomes very complex, right? So it's important to know that. Let's understand a little bit about all of these three capitals. What do we mean by the natural capital? Atmosphere, land, fresh water, ocean, this and that, right? And that ties in very well with what he said, correct? You must make sure that whatever we do, this is never compromised, right? Are we doing that at the moment? Are we taking care that this is not compromised? No. By no means are we doing that, right? Let's look at the financial capital. You're looking at GDP and everything related to that, right? So, and you talk about human and social capital, simple ambitions, right? Doesn't matter where on earth you live, right? The ambition is the same. People want access to education, health, they need to be empowered by knowledge and skill, and they just want to be happy, right? Not breathe air and fall sick. No, you don't want to do that, correct? So, these are the three capitals that you must always take care of when you talk about sustainability. And that's the challenge, correct? So, let's understand what these three pillars mean. Yeah, environment, you must ensure that natural resources are consumed in a smart way, yeah, and they are renewable. And this pillar almost always seeks to maintain ecological integrity and about protection of the ecosystem, right? By being responsible in how you consume resources, right? And that's the reason why there is increasing emphasis on on renewable sources of energy, right? You may consume, but they should be renewable, they should be replenished, correct? Economic, yeah, I think there is more and more reason to ensure that don't worry about tomorrow, worry about long-term economic growth, right? You don't want to do something that gets you money for the next 2 or 3 years, but makes all of us almost bankrupt in different ways, not just economically, over a long period of time. So, this usually ensures that human communities have access to required resources to meet their needs without compromising future generations, of course, right? And social, we just spoke about that. This is simple, the ambitions are not very high, but this is what is impacted the most, unfortunately. For all the sins that others commit, the biggest casualty is the social pillar, right? If you see what's happening in Delhi, for example, right now, right? You don't want that kind of a situation, right? Fortunately, there is now an evolving concept of sustainability. It's not what we used to think earlier, right? So, my earlier cartoon showed this. So, this is a very narrow-minded way of thinking, right? As opposed to that, we are transitioning from what people like to call this intersecting mode of sustainability to an integrated mode of sustainability. What does this mean? What does this imply? That above everything else, you must take care of environment, right? Next comes social equity, etc. Social. And in the end, right, once you tick off these two boxes, you worry about profit and economy, right? So, this is what is called the integrated model, right, which recognizes that your foremost responsibility is towards the environment, yeah, and social well-being of not just US of A, yeah, let's make America great again, no, not like that, yeah, whole environment, that's important, yeah, and because if you take care of these two, hopefully this follows, right, and I don't know if it's in my next slide or later, but fortunately the industry is also beginning to understand that, at least worldwide. There may still be very narrow-minded businessmen, but industry by and large understand that. So, I don't think I will answer all of these questions when we speak, but all of you, when you're taking a shower or lying in bed, instead of seeing reels, yeah, infinitely, you should think about why is sustainability important? Is there anything we can do, each one of us? Is there anything we can do? Like not printing course notes, that's one of the things, yeah. And how can we do different things in life that make it better? Not for everyone else, for your children, for your grandchildren. Let's just think about them, right? And then everything is okay. If you think you're doing it for someone who's living in Congo or Zimbabwe, then you don't think like that. About our kids, right? Then thinking is different. Because until now, we have always been thinking about economic development. When I say we, I talk about industry, right? Because that's where it comes from. We have been thinking only about economic development, climate change, resource depletion, etc. Let it go to hell. We don't care. There are some leaders of the world who do not even believe in climate change, correct? Dangerous, correct? So, it's a well-documented fact. For example, if you look at greenhouse gases and related emissions, that more than 90% comes from extraction of resources, our own resources of Earth. And the way it is impacting us is in ways unbelievable, unimagined. Yeah, all of you come from different parts of India, I think. Have you seen climate change there in wherever you live? Or are you simply saying yes? Have you seen it change? Yeah? I remember as a kid, I used to spend every summer in Pune. And at that time, we used to think Pune is a hill station, right? Never remember as a child, needed not a blanket, but something to pull over in peak summer as well. Today, impossible, yeah? Touches 40 very casually, correct? So, it is real. You look at parts of the world getting snow in summer, right? Or parts of the world not seeing snow at all, where there used to be mountains of snow, correct? So, it is real. And for that, the UN, in its own wisdom, has set an agenda for sustainable development. Their goal is 2030, you know, but unfortunately, UN is very toothless, right? They can make plans, they cannot implement anything, right? But however, it is very educative to see the dimension of the sustainable development. How many things they talk about? Yeah, we only think about renewable energy and say, oh, but there are so many dimensions of sustainable development which are identified by the UN, right? For us, no time to go into all of those, but it will be available when you scan the QR code, right? Maybe, or maybe I forgot to add this slide, I don't know, but you should look this up, that's important. And statistics may lie, data never lies, in my opinion, correct? Data is always real. So this is data of how temperature has gone up over time, yeah, especially from around 1950, 1960. Is this a big deal? Yeah? Someone may say, oh, 1 degree से क्या होता है life में? Correct? बहुत कुछ होता है. I mean, many things can happen, right? Snow can melt like nobody's business just because of 1 degree. Lot of things can happen, right? So remember this, around 1950, 1960, we have started behaving in not a good way with the earth, yeah? So that is not your fault, because I think all of you except me were born way after that, right? So the disease began during my time, but all of you are also involved now in this game, correct? So almost more than 1 degree difference, right? And I doubt very much personally if it will follow a linear slope. I somehow think this slope is going to change, right? This slope is going to change, right? And that means hell. how have we abused everything? Again, real data, population. Look at how it has gone from about 1950 onwards, right? So it is not a coincidence that you see all this data and look at what has happened to temperature, correct? Or global warming and greenhouse gases and stuff like that. Look at population, look at GDP, yeah, or your desire to make this go up. Look at primary energy use. Look at it along, look at tourism, right? 1950 onwards. This is unreal, yeah? People want to travel like crazy, which is not bad, but you must find a good way to travel, correct? Everybody driving a car is not okay, yeah? If you can avoid it. Public transport, if you can. But then the responsibility is also on local governments to provide access to public transport. I cannot say take public transport and there be no public transport available for miles together, right? So we are therefore tackling a huge problem, correct? And not one single person or one single government can solve it. But I'm going to give you an example of how the Swedish government is doing, because that's where I come from, right? So in 2006, now almost 20 years ago, there was a Swedish law that all universities should promote sustainable development in their education, right? At least people should understand what sustainability means, what its dimensions are, and all the universities in Sweden do that already, right? And they've been pretty ambitious. Whether you reach those goals or not is a different matter, right? But the bar is high, right? You don't want to be a world-renowned high jumper and put the bar there, right? Where I can just go like that. No. You need to put the bar high. And the bar is very high, that by year 2025, there will be no greenhouse emissions, right? Will they reach that? I can almost guarantee that they will not reach that, right? But no problem in having the bar high. And there is also, because of such laws, and especially the young generation getting involved, yeah, through what we do in universities, there is huge public opinion around global warming and what governments can do or what industries can do and cannot do, right? Which is nice, right? So I will not get into details, but some points to note that the Climate Act of Sweden kind of tries to ensure that nobody will interfere with the climate system, right? Protect it. And there is, of course, resentment among the public many times, because the public then asks, why should we be the only people who should pay for the world's problems? Is the rest of the world doing that, right? And those are the kind of challenges. If the population starts getting inconvenienced and say, nobody is doing it, but I'm paying a price, yeah, then they change very quick, correct? And for that reason, it's important that all countries do something similar, right? To the extent that they can. So let's see what the climate targets have been. When this was signed in 2008 or whenever, the ambition was that the emissions should decrease. I told you no emissions by 2045, but should decrease by 40% by 2020, 63. I mean, these are all documented in the law, right? 100% in 45 means 85% reduction and 15 by way of compensation, right? Like you do something, you plant trees, you know, you return the carbon credit sort of, right? Where are they now? 29% compared to 1990 level. Target was 40. What do you think about 29%? Yeah, will you criticize that, oh, you are barely 75% of the target? Will you Will you criticize that? Or will you say that 29% is pretty impressive to reduce from 1990? And I think 29% happens because the bar is at 40%, which is unrealistic, but the bar is high, correct? So they may not get anywhere near that, but let's say by 2045 they are at 50%. Not bad. At least some tangible difference is happening, correct? So I don't want to go too much into this. Maybe some of it is in your similar, 1950, 1960, where it begins to go wild and cause problems, right? And therefore, extremely important that we keep this in mind, right? All of them show this crazy trend at about the same time, right? So enough about that, yeah? Please, please, please think about this, at least on a weekend, or but do think about it. Let's look then at traditional manufacturing, yeah? This is how it has happened, yeah? Take resources via mining or whatever, right? Make the raw material that you need out of that, right? Use it to fabricate products that give you joy and luxury, or sometimes it could even be necessity, I don't know, yeah? So take, make, use, and then junk it, dispose it, right? Is this sustainable? No way, yeah? You cannot sustain it. And that's the reason now you will see all the buzzwords, but they're really not buzzwords, right? What are some of the buzzwords related? Circular economy, yeah? Recycle, reuse, correct? All of this you will hear more and more of, right? But that is important, correct? When we now talk about manufacturing and sustainability, it needs again to take care of the same three pillars, right? The manufacturing also should ensure that you are doing it in an environmentally benign way, yeah? Still provide the public with what they need, and take care of economic aspect as well, so that industries thrive and survive, right? So if you want to do it in a sustainable way, you can look at probably reuse, remanufacture, repurpose of raw materials, look at reducing manufacturing cost, look at energy consumption, right? I'm not getting into detail, but you can see that slowly we are coming towards additive manufacturing somehow, right? In a strange sort of way, right? You want to be able to have the design freedom so that you can make your parts lighter. You want to reduce wastage, right? So all of this is slowly pointing towards the merits of additive manufacturing, right? And that's the reason I thought I should spend some time. Yeah, so essentially different ways of saying the same thing, right? But important for us to manufacture sustainably, right? And do keep track of that. According to me, the nicest thing that is happening right now is that companies are beginning to realize that there is substantial financial and environmental benefit that results from sustainable practices, yeah? Environmental benefit, I think companies always knew that if I do something in a right way, there is environmental benefit, but maybe I don't care about it. That used to be how they thought. But now they realize that there is also financial benefit. How many of you have taken flights recently or booked flights? Many of you? Yeah. How many of you have seen your flights when you book indicate what is the carbon footprint for the flight? How many of you have seen that? Anybody seen that when you're booking there is carbon footprint? Yeah, I'm traveling from Gothenburg to Frankfurt, Frankfurt to Hyderabad. What is the carbon footprint, right? They mention the carbon footprint. Some companies, and that's where the financial part comes in, they also make you, or not mandatory, but they ask you, would you like to pay a certain amount, yeah, to pay for use what you're contributing to the carbon footprint because of your travel, right? Little bit, correct? So you see suddenly that change happening around you, right? So which is, I think, a positive sign, yeah. Almost all of them now realize that it's also a saleable thing, right? One of our biggest projects, we will get to that maybe when I talk about coatings, is for instance, to find an alternative to cobalt, right? So we have a large project from one of the biggest powder manufacturers in the world, Höganäs, which is a Swedish company, and they're giving us lots of money to see if we can make as good coatings but not use cobalt. If you look at wear coatings today, the most popular coating is tungsten carbide cobalt, right? So the first goalpost for us is to avoid using cobalt, yeah, because that has many sustainability implications. Cobalt is on the list of EU's critical raw materials. So is tungsten actually, right? So so that is step 2, because it is harder to replace. Cobalt is slightly easier to replace, correct? So you do that. And for that reason, I think it's nice that companies begin to think differently about sustainability, and many of them, at least the big ones, now consider that all of these are a part of their corporate social responsibility, which is nice, no? They think that they should not just look at the financial bottom line, but also consider both social and environmental performance of how they produce things, how they recycle things, and suddenly for that reason, people are beginning to wonder about batteries, for example, right? How do you recycle? Where does the lithium go, right? You're using so much lithium for your batteries. Where would it go eventually? Once the batteries reach their end of life, what happens to them, right? So a lot of emphasis on things like that, which is important. So if we are going to count on our fingers, what should we prioritize when it comes to sustainable manufacturing, or what are the main benefits? Lower resource and production cost. Lower resource is obvious. Lower production cost not so obvious, yeah. But that's something we need to keep our eyes on. Lower regulatory compliance laws. There are more and more regulations coming out now, which will insist that what goes into your product is sustainable. Otherwise, the penalties would be heavy. And it's important that the penalties are heavy, or something like hard chrome. People have complained or legislated that we should not use hard chrome for a long time, but is it implemented? Not yet, not in many countries, right? So that's there, yeah, and yeah, various other things. So that's important. And as I said, the most refreshing for me is how the companies approach sustainability. Companies of all sizes today, right? That leads to improved, not just resource footprint, but also in many ways better performance. And then, yeah, and that is what is spurring innovation. The reason we get research funding is to a large part driven by the fact that these companies want to become sustainable, right? We are at the moment spending a lot of effort at least on these 3 R's, right? Being able to recycle, right? I'm just showing cars here, but it's only an illustration. But in all product life cycle kind of issues, we are trying to see if we can recycle at end of life, whether we can reuse, right? Or we can somehow recondition by taking it back to where it started, right? In some way. There's a lot of emphasis on that, right? Some examples of how it links to manufacturing. Lightweighting, right? That's a big plus from additive, or to go from steels or super alloys towards aluminum, magnesium alloys. What's the big deal with lightweighting? Why would you want to lightweight? Yeah, why would you want to lightweight? Reduce it? Almost correct. Energy use, efficiency, you said something? Reduce cost, yeah, a little bit, yeah. So it's different things for different applications, right? If you're building the same part out of the same material, yeah, but using less material, I mean, that way of lightweighting is one thing, right? Using lightweighting so that your emissions are lower, like in gas turbines, that's another reason for lightweighting. But all of those eventually, this is nothing new. I'm just listing it out here for you. But we can do all of these things with or without additive manufacturing, let me say, right? But additive manufacturing is an important cog in the wheel, so to speak, right? So if we can do, we can use additive manufacturing, you can, easy to imagine that through appropriate design, this part is easy to tick off, yeah? If you do coatings, this part is easy to tick off, right? This is related to those two, so that's easy to tick off. So many of these automatically happen because of additive manufacturing and because of using coatings to extend life and therefore not having to replace parts so frequently, right? So that happens, by the way. Now this is something which is an enabler for additive manufacturing in particular, right? Doesn't matter where you start, better performance of products, right? I mean, if you take a turbine blade with very intricate cooling holes, it used to be a nightmare earlier, right? You make a turbine blade out of supposedly the hardest, one of the hardest materials, like nickel-based super alloys, and then drill a hole through that. Not easy, right? But now you can build it into that. So much better performance in that sense and functionality, right? Very simplified manufacturing. You can imagine the trouble in machining of super alloys, right? Extremely hard, can do that. And then reduced costs, of course, apart from the fact that you are saving so much material, right? By using a bottom-up approach rather than a top-down approach, right? I thought this is something I must put up, right? For a moment, imagine that you are not reading the rest of the text. Is additive manufacturing sustainable always? I think this is crucial. It depends, right? It's not always, so you cannot close your eyes and say, okay, I'm making this lid today in some way, tomorrow I'll start additively manufacturing that. No, it's not always sustainable. It has potential to offer sustainability by doing these things, right? But the manner in which you produce could be consuming more energy, right? So there's a flip side to it. You may use less material, you may make your parts lighter, but you may be consuming lot more energy in accomplishing these two, right? And then it's not okay, right? Therefore, you should not be fooled by someone who says that everything you can additively manufacture. Doesn't work like that. Yeah, and for that reason, this is crucial, right? You must be very clear where a certain component or a certain component that you are now able to design in a particular way because AM is available, and you know that I won't have to machine it like I used to traditionally do, and therefore it opens itself to new ideas of design. Yeah, so if you do that, then maybe there is a lot of benefit to be had. But if you don't do that, it doesn't automatically mean that what you're doing is sustainable. It could be quite the contrary, right? So that is why we have one of the talks from an invited guest speaker focusing on design for AM. Yeah, this is a big field at the moment, right? So he will speak for an hour and a half. I don't know if that's enough, right? But you must all know that this is crucial, right? In some cases, AM makes a lot of sense. In some cases, it may make no sense at all. And that's one of the things you must remember. There is always a tendency, especially on part of researchers, right, or academic guys like me, to say that whatever I do is the best, right? That's not true. If I work on AM, AM is not always the best. If I work on thermal spray, it's not always the best coating technology, right? In some cases it would be, in some cases it won't be, right? So as a designer, it's up to you to make that judgment in a good way, right? So be sure about that. Since we are covering both AM and coatings, I also wanted to quickly touch upon how a coating technique. I'm taking just thermal spray as an example because I have mostly done thermal spray in my life. I like it. I like how versatile it is. But what can it do? It can reduce emissions in operation by, for example, allowing you to operate a turbine at a higher temperature. If you do that, you automatically reduce emissions. And one way of doing that is putting on thermal barrier coating. It can extend component durability. How do you do that? By putting on coatings which are wear resistant or corrosion resistant or resistant to whatever makes a component fail prematurely in real operation. Yeah? It can reduce material usage as a direct consequence of this. Right? If you extend life, you have less shutdowns, you throw less of your components, and therefore you reduce material usage. You can lightweight, right? If you want a certain functional property, right? For example, you are using some material today because it is highly corrosion resistant. Yeah, you don't need to make the whole component out of that material. Now there is better appreciation that you can use something else underneath if you have the ability to put on a good corrosion resistant cover around it in the form of a coating, right? Usage of environmental friendly materials. I was talking about replacing cobalt, but there are many other such issues where coatings allow you to do that. Many things. Repair is a big thing, especially for materials that are not well endowed in Mother Nature, right? So you can, it's important to be able to repair rather than junk, right? So this was my very short overview on sustainability and how it relates to manufacturing, whether it's AM or coatings. This is a huge field. My only request and ambition would be that you guys think about it, right? There are, for each technology, there is a sustainability angle to it, right? So do think about it, and be agile and well-read, yeah, rather than believing everyone, including me, right? You should do your homework when it comes to matters like this. Any questions? Or yeah. Yeah, I mean, it's a very complicated question. Neither I can answer it nor you can answer it, right? Uh, you can choose to stay away, but this is everyone's game, right? But you're asking me the same kind of question that my colleagues in Sweden ask. Yeah, why should we be forced to go into electric vehicles and this and that, and why should, because of Sweden putting a law saying that by 19, whatever that date was, 2050 or 2045, we will be emission free. Why should we pay for it? Yeah. And environment is not something like, okay, if Sweden does that, then what Denmark does, India does, rest of Europe doesn't bother. Sweden is safe. No, it's not like that. It's a global thing, right? So, and you're absolutely right in the sense that there are local compulsions, right? And that is why it is challenging. If everything was local and the benefits were also local, then it won't be such a problem. But the benefits are global, so the price has to be globally paid, yeah, and that's why it doesn't have an easy answer, unfortunately. Maybe you become a Prime Minister of India someday and answer that question.
Second question about cobalt. Most of the cobalt is controlled by China. Supply chain of cobalt is controlled by China. So what is your take on that? Like, Europe wants to get away from cobalt because of that.
Hey, don't ask me militant kind of questions, but what does control by China mean? Do you know where cobalt comes from in the first place? Where? Correct. 70% of cobalt comes from Congo, right? So forget about control and stuff, etc. It's just about dependence, right? If I am even any manufacturer and you are the only guy selling raw material to me, I don't like that. Yeah, I don't care if it is China, Africa, or even India itself. But if you are the only producer of that raw material in India, I don't like that, because I open myself to blackmail tomorrow. Suppose you sit there and say, oh, Joshi sahab, aapko to main ye bechunga nahi, right? What do I do? Or if you suddenly say, from tomorrow morning, because 26th of November is a good date, auspicious date, I am doubling the price of my raw material. What will I do? Yeah, so it is.
EV is controlled by China. Cobalt production is controlled by China.
Yeah.
Because of geopolitical issues, what will Europe do?
Yeah, they will do what they are doing now, which is to find alternatives to cobalt. That's the way out, right? But you're raising good points, and to some extent they also motivate what we should be doing, rather asking these questions, right? Yeah, if Europe is imposing tax on India for carbon, what alternative does India have? Can it say that, no, we will not pay tax, we will not have anything to do with Europe? Can it say that? You meet me over lunch, we will discuss more. Yeah? Anybody else? Yeah? But think about it, that's important.
Sir, moving towards electrical vehicles, does it really reduce the carbon footprint?
On the face of it, yes. But then people are slowly realizing other issues. Maybe it reduces carbon footprint to the extent of driving your vehicle, right? Going from place A to place B, not using gasoline, using, yeah, it reduces the carbon footprint. But what about other issues? Extracting lithium, disposing lithium, right? What is the cost attached to that? And I think nobody has a good answer. Suddenly it is hitting them in the face, and we need to do something about that.
Producing the electricity somewhere.
Yeah, correct. Yeah, right. Absolutely correct. Yeah. So this is very complicated, and therefore it's also very multidisciplinary. Yeah, we as a manufacturing person should not pretend that we know everything, right? And that's why I wanted to, in an additive manufacturing course, wanted to make that point, that additive manufacturing is not always sustainable, right? I mean, and we should not pretend that it is, right? So, but thank you for listening. Let's yeah, let's move on. Let's move on to what did I have to do now? Yeah, let's talk about dive straight into AM. Yeah, and oops, sorry. We can continue, right? Nobody needs a little break or anything, yeah? So, so first things first, I'm going to focus almost entirely on metal AM, yeah? AM is too huge, yeah? I don't want to get into stereolithography and that kind of stuff. So, we are going to stick with metal AM just for convenience, because there is not that much time. I hope that's okay with you, but if you feel like discussing something else, we will, of course, discuss it any other time over the next 5 days. Yeah. So I'm not shying away from anything. I'm just trying to see how I can use my time well.
They are related to a lot of other factors.
Yeah.
What he was asking.
Right. Correct. Yeah. So all of you know this. At least I hope you do. Right. When we talk about traditional manufacturing routes, there can be many different aspects to that. It could be subtractive. We will touch upon it a little bit, such as machining, drilling, milling, etc. It could involve separating it from a larger body, like cutting, sawing, there's casting and forging, welding, brazing. All of these are important. Yeah, I want to make that point. It's not as though now AM will start and all of these will go for a toss, no? So, but these are traditional techniques. They will be there always. AM seeks to replace some of them, some of the times, right? That's important. I don't think we need to go into this. All the subtractive techniques, for example, are bottom down. You start with a huge chunk of material, and then from that you machine out in an elegant way as well as you can the kind of part that you want, right? Additive, on the other hand, everything you have heard of, layer by layer, top down, right? So you kind of use what you need. You don't create junk alongside that. A simple way of doing that, right? Let's see. I always like to see the definition. How do people define AM, right? So if you look at the International Organization of Standards, right, they define AM as follows. The process of joining materials to make parts from 3D model data, usually layer by layer, yeah, as opposed to subtractive manufacturing and other formative manufacturing technologies. Yeah, you have many categories of AM today. If you start Googling, you'll see all sorts of stuff come up, yeah, which somehow fulfills at least some parts of this definition, right? Powder bed fusion, all of us tend to accept that. Directed energy deposition, and I intentionally sequenced it in this manner, yeah. Binder jetting, material jetting, yeah, little less used. Material extrusion, yeah. I honestly, I didn't know that this is classified as AM. I didn't know that, but apparently it is. Sheet lamination, what the hell? You stack these sheets together layer by layer, so it is AM. No, I don't agree, but I must tell you what is out there, right? Vapor this goes into a regime which I said I will of course not cover. Yeah, but be that as it may, for me, what is relevant the most from a metal additive manufacturing standpoint are these two: powder bed fusion, directed energy deposition, right? So we will spend most of our time talking about these two, right? And if something else is interesting for whatever reason, we will take it over lunch, tea, or at the guest house, yeah? So, guys who are wedded to AM always like to talk about this: wide-ranging benefits over traditional manufacturing, design freedom, reduce material wastage, shorter lead time. The reason I decided to pick these three and not go through a long list about sustainability, this and that, is because I believe in these three, right? Whether it is sustainable or not sustainable is a different issue, but these three are always true. Yeah, there is no ambiguity about the fact that if you do something by AM, it gives you immense design freedom, right? Which therefore leads to lightweighting and things like that. Yeah, there's no two ways about that. If you do something bottom up rather than top down, via machining, drilling, all that stuff, you don't produce this kind of wastage or scrap, right? No confusion about that either. And therefore it leads to shorter time. And any of the advantages that are directly related to these three, I agree with, right? I will stay away from sustainability because I relate that to design specificity. But otherwise, if you say, okay, I can print just in time, yeah, of course. I can make patient-specific implants, right? I have a Swedish colleague who is 7 feet, and I have a friend from my BTech days who's struggling to reach 5 feet. They want different hip joints or dental implants. You can make patient-specific implants, right? All of those benefits are pretty clear. So no point in arguing about that, right? You use all the tools at your disposal to make it happen, right? So you have design data. This is something going on the side, but you rely on digital data. You rely on good quality feedstock, yeah, and you rely on an appropriate heat source to make metal AM happen, right? Now, we will at different points of time talk about all of these three, right? During the course of this talk. Feedstock will be part of a different lecture perhaps, but you harness the benefits from all of these three to be able to do crazy stuff like that, right? In a very convenient way. In terms of size and complexity, what can you do, what can you not do, right? I think that is controlled entirely by your imagination partly, and partly by your designing skills, right? That is what limits it. Otherwise, you can do just about anything, right? This is something that NASA does, but right in the same building where I sit or have my office, GIAN Aerospace makes similar looking parts which are taller than this guy, yeah, by DED wire, right? And they fly, yeah. So just like some people may try to sell you that, oh, AM is, if you use AM, you're sustainable. That's wrong. There are other guys who will tell you that AM is all hype, not reality. There'll be other guys who will tell you that as well, right? Even that is not reality, right? And as educated people, our job is to filter what this group is saying, filter what that group is saying, and kind of zero in on reality, right? So the reality is somewhere in between. Yeah, yes, usually it is sustainable. It's not hype, it's real. But in some cases, it may be meaningless to look at AM as an alternative production route. Yeah, and this is also important to note that all of these are realizable, yeah, using appropriate tools, right? So you can do many, many fun things at different length scales. That's important, right? Because I've heard people say, oh, AM is okay, like for only small parts. Yeah, small parts because you're looking at PBF. Maybe you have a 9-inch by 9-inch or 6-inch by 6-inch build volume and say, okay, we will do only small parts. No, these are real, they fly, so no problem. So how does a typical AM process flow look like? I'm being a little generic here, but identify the part, yeah, and somewhere in between, I will say, decide if that part is appropriate to be AM built, right? First of all, right? And if it is appropriate, you identify the AM process. It could be one of several that we will talk about, yeah. Prepare a CAD file for that, yeah. Do a layer by layer slicing, so that you know how to print, then actually print and post-process, right? So we are going to talk about several aspects of this in different modules of this course, right? Incidentally, I took some of these slides from my postdoc, Ashish, very smart guy. He's in Finland right now. So we'll talk about most of these things. So at the moment, this module and the next one, we will focus more on the printing part, right? So what concepts do you need to know, yeah, to exploit AM? You need to know about the raw material. What quality of powders do you need to use? What quality of wire do you need to use? In some cases, it could be liquid, but we will not talk about that. But powders and wires especially, right? You need to better understand how melting and solidification takes place, right? In some cases, and we are not going to talk about that either, you want to see if you can take some signals from here, right, during melting and solidification, learn from those signals and do some sort of a feedback loop to be able to control how you print. Yeah, that is crucial. You want to do sometimes, depending upon the application, some mechanical post-treatment. I'm going to differentiate this little bit from some post-treatment that is inevitable to make the part, depending upon what process you use, but something that you need once the part is out to actually deploy it in real use, right? So it could be mechanical. In some cases it could be thermal, yeah, and we will talk a lot about this part. You also need to understand characterization of these parts. I don't know how many of you come from a metallurgy background. How many of you have seen the structure of an AM part? If you can raise your hands. Have any of you had a chance to see the structure of an AM part? You two, but that's rare. Anyone else? 3? Yeah, but very few. Most of you others have not, right? So it's important for you to be aware of how the process or the process parameters you adopt, how do they influence structure of the built part, yeah? For some of you, it may just be curiosity. For some others, it may be something that is very important because, believe it or not, this eventually reflects what mechanical properties the part will have. Yeah, I see Dr. Manjaya nodding, so probably he does a lot of that in his research. And then after all this, you need to see whether what you have built, can it sustain a real application for a long time, right? If it cannot, does it need to be surface engineered, right, in some manner? So if you want to fully exploit AM, you need to have a fairly decent understanding of all of these things, right? Sometimes you may not, but someone else in your team might have, or you may collaborate, but the important thing is all these things are crucial, right? And I spoke about structure. uh, the metallic structure of this. That was just one example. Someone like Dr. Manja is necessary with good background in materials engineering. I think the 2-3 hands that went up also are in some way associated with materials engineering. So different parts of this cycle require different kinds of expertise, right? Data science, design, yeah, robotics and automation. You need knowledge of all of these, right? Does anyone want to argue about this, right? That it is interdisciplinary or whatever. Powder metallurgy, how do you make the powder? Yeah, is what people say that it should be completely spherical, the powder particle. Is that true? Or you can manage without that? Is it a sales gimmick that powders must be absolutely spherical? It should have 0 islands, no, each particle. So if you touch all these bases, then you are more competent to answer all these crazy questions, right? If not, you can still survive, but then you have to believe in whatever someone is saying, correct? So that's important. Let's look a little bit at what the canvas looks like, canvas of additive manufacturing technologies, right? So there are essentially 2 broad categories, one associated with electron beam. Different kinds of electron beams could be laser, energy beams. One could be laser, one could be electron beam. The other, of course, is arc. People used to call it a poor cousin of the energy beam technologies, but I don't think so. Fairly proficient in, let me see if I can, this is incidentally what I'm showing you here is everything that we have in did it start or did but doesn't matter, it's not important. Yeah, but what I wanted to show while that video is going on the side is we at our university have access to all of these things that I encircle here, right? We have an electron beam equipment from GE Additive. Earlier it used to be known as RCAM. It still remains one of the very few companies that makes electron beam powder bed fusion equipment. We recently have procured a powder bed laser equipment from Aconity. Has a fairly good size build volume. We have also been working for the longest time, even before it was fashionable to call it additive manufacturing, for almost 20 years now. We have been working with direct energy deposition using wire. And this big part that I have mentioned, made by GIAN Aerospace, is an outcome of some of the low TRL work that we did with direct energy deposition during wire. So we touch all of these bases. More recently, we have been beginning to pay more and more attention to VAM also. It's not as useless as people want you to believe. It's cheap, but it's very useful. And we have begun to use it to make, at least in a preliminary way, many gas turbine parts and things like that. Yeah. Have any of you seen an EBM machine anytime, anywhere? There are very few in India. There are more SLM machines, I think, in India than EBM machines. No, but I will try and run you through how this works a little bit. Yeah, so if you look at an electron beam machine, as the name suggests, it uses an electron beam as an energy source, right? and powder as feedstock in most cases, right? To 3D print any metal component. We are going to focus now on a powder bed, right? What do you think a powder bed fusion means? Just guess from the name. What is powder bed fusion? BTech. What is powder bed fusion? Yeah. But then what is bed fusion? Forget about powder. Yeah. Not too hard to convert, not too easy to break. You're MTech, guys? BTech only? With the help of UV rays. In this case, I have already said we are using an electron beam. So it's okay. Yeah, but MTech. So, next step, that's correct. So you use the powder, you make it in the form of a bed, yeah, and you use the electron beam to locally fuse in regions of interest. Those regions of interest being dictated by what your 2D slice looks like, right? So that's simple, right? So let's talk about some of the hardware issues. I actually had a full video of the RCAM equipment we have, but I couldn't accommodate it. So this is what it looks like. It's somewhat a lab type equipment for EBM. It has two essential parts. It has this electron beam column, just like you would have in an SEM, for example, if you have seen a scanning electron microscope in a very loose sense, something like that. Yeah, and then you have a processing chamber which has twin powder hoppers where you feed the powder that you will utilize to make the component. It has several other, the hardware has several other crucial components. It has a rake. What's a rake? Yeah, it will take the powder from the hopper and form a bed with that. Yeah, it will spread the powder. So that's a rake, right? And then the electron beam will locally fuse the powder, and then the rest of the powder will go away, or it will remain unsintered, not go away, I'm sorry. Then this stage, there is a, you start with what is called a build plate, and then this will advance depending upon what your layer thickness is. Again, a new bed of powder will be raked. Again, you will locally fuse. Maybe this, now what you fuse would be a little bit different compared to the earlier layer, because again it will be governed by the slice data. So, and that's how it proceeds until you have built the part that you have designed to build, right? So, just what I said, thin layer of powder distributed and welded, every layer. Part size is limited, as I was saying, to whatever your equipment allows you to handle. You can't build the kind of cone that I showed right now in such a chamber, yeah. And eventually, whenever you stop, the whole build volume will be filled with powder, with the component kind of embedded inside, where it was sintered by the beam, right? So, or fused by the beam. I have some videos. I don't think they do justice to what actually happens, but it's a very interesting process to look at, right? One nice thing is the electron beam that moves, it moves so quickly that you can simultaneously maintain several melt pools at a given time. If you don't believe me, I hope there is some video that will show you that, right? So it's so quick that there is something molten here, here, here at the same time, because it's moved so quickly, right? And that is extremely fascinating. Here is an example where you have a rapidly melting line at different segments at a given time, right? So that works very well. And how do you move this point? Yeah, that determines structure. So on the face of it, it's very simple. At another level, it needs some significant knowledge of what will happen depending upon how you jump these little beams around, right? So, and then eventually once the process is done, the sintered powder with the build parts will look something like this, yeah? Looks like crap actually, it looks very bad, right? But once you take the unsintered powder out, once you have removed that, then you have whatever you want. This may look like a very unimaginative build, right? Not terribly exciting, but as an academic, this is very exciting, correct? Why is it exciting to do something like this? For various reasons. We are trying to build here blocks, yeah? So we are looking at different build strategies, right? So this may be built with the laser beam dancing around in a certain way. This could be built with the laser beam dancing around in some other way, right? The size is such that we can, for example, do tensile test specimens or fatigue or creep. We can fabricate them in this direction, or we can fabricate them in this direction, right? Why would we want to do that? Why do I want to build a tensile specimen like that, fabricate, and why do I want to do it like this? To study what? Strength. Yeah, I'll make tensile specimens to measure tensile strength, but yeah, that's not the answer I'm looking for. Loaded direction, correct. So go one step further, then you get 100 out of 100. Anisotropy, correct. Yeah, I'm interested in seeing if the mechanical properties are same in the build direction and the direction transverse to it, yeah? Because many of these, at least reportedly, tend to be very anisotropic in properties, right? So that's what I want. And then I also want to look at what happens if my wall thickness is thin, thick. So this kind of a build allows me to do many things, right? So this is a bread and butter build we call. If we make one build like that, it's one PhD and little bit of a postdoc, right? So one build like that keeps us busy for a long, long time, yeah? And then, of course, it need not be like this. It could be more complex, and you can build just about anything, right? So that's important. Let's look at some other things. There's a heat shield here, right? For preheating, we have couple of, I told the rest of you. Yeah, vacuum. So this is done under vacuum. We have roughly 10 to the minus 3 millibar level of vacuum, and the nice thing is there are only two moving parts. One is the rake that comes and sweeps the powder. The other is the bottom platform that goes up and down, mostly up, yeah, depending upon what layer thickness you have, right? So, anything else? Yeah. So, then all of you know what the purpose of the rake is, to apply a thin powder layer. Now that is a process variable, mind you, right? How thin do I make it? Do I make it 30 microns? Do I make it 50 microns, 60 microns, right? So that is something I can vary, and that is one of the process variables that people usually investigate, right? And your Z direction, up and down motion, will be dictated by what powder layer thickness you choose to employ during your build, right? Let's talk a little bit about the process then, right? And there are some, hopefully, videos that fascinate you. So you always have a support structure on which you start building. What does it mean? Eventually you need to take it off. Yeah? You need to remove the support structure, right? And your your geometries could be as complex as possible. There is usually no constraint, but they have to be within the build plate that your chamber can accommodate, right? So that's the main thing really. So the typical layer thickness that we have used in most of our work has been between 50 to 90 microns. Sometimes that is also dictated by your powder particle size, but that's a complicated interrelationship. But we have kind of changed it during this over this interval, and that works quite well. So if you have to define the steps involved in processing, right? So it starts in powder bed fusion with application of a layer by a rake with whatever thickness you choose. Then you use an appropriate power for your electron beam. Yeah, we usually use something of this sort, which can be varied about 3 kilowatts at fairly large speed. We can vary the spot size as well. There is a certain focus spot size for the electron beam, but you can defocus. If you choose to build it with the electron beam gun little bit further away from the focal distance, then you get a defocus spot. Sometimes you may want to do that for certain kind of applications. And then you program it to scan. So the scan strategy is important in how you make this beam jump, and then depending upon what material you are depositing, you govern the temperature that's there as well, right? Our experience with our equipment has been that you can maintain up to 40 melt pools at a given time, right? So the beam is jumping, but what is melted is not yet fully solidified, right? And that's what it means. It doesn't mean 40 beams, right? It is 40 live melt pools, yeah, which gives you some indication of how fast the thing can move. Yeah, and these are basically research interests. What is the influence of power? What is the influence of scan speed? Do we do it in focus or non-focus? But just talking here about the capability of the beam, right? Now Dr. Manja has showed me the trick of how to make my videos work. So this is powder raking now, right? So then little bit of preheating and sintering, yeah, using a laser beam, and then we do a contour. We will stop there and see if you understand what contour means. So we preheat to sinter the powder, then we do contour melting, yeah, and then we do hatch melting after that. Yeah, very fascinating to see, right? Yeah, so many electron beam spots. Yeah, so this is still all contour melting, and then we do hatch melting, right? So that is hatch melting. And usually the parameters for melting the contour are different from parameters for melting the hatch. A contour is not always necessary. Yeah, so just going by English language, what is contour? Yeah, please. No, it's actually taken by a camera. Yeah, it's real. No digital.
Digital image correlation
For what?
when inside test is happening, how much strain hardening we are capturing by using a live cam like that we have done?
Yeah, so this is just a live camera. Yeah, so does that answer your question? I'm not clear about your question.
Means, what kind of camera we have?
I will have to get you those specifications. I don't off the top of my head know what camera, but yeah, it's an IR camera. It's a pretty fancy camera as well. But if you want more details, you have my email. Write to me. I'll get you those details. Yeah. So, coming back to my question, what do you understand by contour? Exactly, right? So, it's not mandatory, but we usually like to do the outer periphery of the part first, yeah, and then do everything inside that boundary, which is called the hatch. Usually the parameters that we deploy are different for the contour and for the hatch, but yeah, we see that that works quite well. I'm not going to go full screen because I don't want to go back and forth. Yeah. So at the end of this, imagine that I have raked, pre-sintered, done the contour, done the hatch, one layer over, right? Then I repeat that. New raking of the powder layer, same steps follow. Once everything is done, yeah, as per your CAD drawing that you have kind of transported to this equipment, what you eventually get is a sintered block of powder, right? Embedded in this powder bed, yeah, a sintered part, right? The sintered powder is subsequently removed by grid blasting. The rest of the powder is just, it can be recycled, right? We will come to that in a minute about recycling of the powder. But yes, please. It depends little bit. Again, that too is a parameter of control. Yeah, but you're right. It is not required every single time because the bed is already hot. That's your question, right? The bed is already hot, and depending upon what you're building, if we do Inconel, sometimes the bed stays at 1000 degrees for the entire duration of the bed. So it is pretty hot, and that's a good point though. So we don't always use it. You can use it if you want. As with everything else, it's a parameter that you can play with. Yeah. Bed is heated. Yeah.
No need to heat every layer, preheat every layer. But if it reaches certain height, furtherly does it require to preheat?
Yeah, that's what I'm saying. It's little bit up to, it's one of the parameters you can choose to heat or you can choose not to heat, depending upon at what temperature you are maintaining the build and whether or not you think preheating is necessary and helpful. Yeah. So, if you just finish printing, what you see is very unattractive. No, it looks like this, pretty horrible. Yeah, but it's not so difficult. You then just use a grid blasting machine. Take the rest of the unsintered powder or loosely sintered powder off. Yeah. What we do many times is use the same powder for blasting as we are using for the build, right? So that there is no contamination. So we do that sometimes, right? This is exactly what you had seen earlier. But if you saw it right after building, it looks horrible, right? So rest of the powder. What are your thoughts on what happens to the rest of the powder?
It can be reused.
Reused forever. How long? 2 or 3 times. Why not 4th time? Overheating melts the powder. Okay.
Again, it becomes a solid piece.
Oh, but then you can't use even second time. If you're saying it forms a solid piece, you can't. So. If you use it again, it doesn't have strength. And what do you say? It depends. Yeah, that's always best phrase in English is it depends. For any, for any question, you ask me anything, I'll say it depends. Yeah, and you're usually right. 90% of the time you're right. Yeah. So in this case also you are right. It depends. Yeah, but jokes apart, uh, some of the powder can fuse together a little bit, so it could be coarser. So depending upon who is using this, some people choose to sieve it, yeah, and remove the coarse kind of aggregated particles, because otherwise it's not good for the properties of the build. The other disadvantage over time is something that I am looking for you to answer, any one of you, UG, PG faculty. Yeah, so size I sieve every time, right? So I get the same powder particle size every time. Yeah, there's little bit of oxidation. Yeah, every time you use the powder, there's little bit of oxidation. Again, it depends. Yeah, it depends upon what powder, but there is little bit of oxidation. You also made a good point. If you are holding the bed at temperature for a long time, depending upon how complex or how big the build is, then this powder is being heated for the same duration of time. Yeah, so that has problems as well. Apart from oxidation, you could, again, depends on the chemistry of the material, but you could begin to see some precipitation, yeah, like carbides and all. So a lot of things happen. So different users have different protocols. Some of them just blindly change it every 3 times or every 5 times, but almost all of them replenish. They decide how much virgin powder and how much used powder should go in each build, right? So, but this one, yes. Yeah. But 10 to the minus 3 is still, yeah. Yeah. And the other, if you are talking about nickel-based superalloys, some precipitation is also important. How do you cool it off? Cool it down. We usually let it happen in the furnace itself. Yeah. So we don't do so much to it. We let it just go on there. Yeah. Cool it, come back next day. Yeah. And do that. Yeah. So there is a, yeah. But sometimes we kind of purge it with argon. I mean, there are different ways. And 10 to the minus 3 is not such huge vacuum, yeah, in a sense, right? But sometimes we purge argon, and yeah, good point. Yeah, I'm honestly not going to talk about post-processing so much here, right? In the sense that I will cover in the other module. But here by post-processing, I largely mean how do you remove it from the base plate, right? So to that extent, post-processing. So you can, depending upon how you have built the initial layers, you can just yank it off from the base plate. Many times you have to actually cut. If you are doing nickel-based superalloys, we many times EDM wire cut from the base plate, right, and remove whatever support structures there are. These other 2 parts will be a part of the other module, right, that we will talk about. If you look, we spoke about the structure a little while ago, structure of the part. The surface would look something like this, right, depending upon, yeah, how you have built that. I'm not suggesting that this is the best or the worst surface morphology, but it could look a little bit like that. Yeah, where you see islands which are fully molten, some that are not, but will melt the first time you do the next one. Yeah. So if you have to summarize, EBM is slightly a hotter process compared to SLM, right? It has low oxygen content in the chamber. The prominent steps are raking, preheating or sintering, contour, hatch, and then remove the build plate and kind of blast it off. Yeah, you can do switching today from, let's say, 718, tomorrow doing CM247 and then hashed alloy, and then suddenly someone says, thoda steel SS316 kar do, that's very hard, right? Because you need to clean the whole chamber, and when we are working with gas turbine especially, they don't like us to touch other materials. So if we start Inconel, we stay with Inconel for a long time. If we move to Tie 64 or something, we stay with that for a long time. Yeah. So, but that is a style in which our group works. It's not a limitation of the equipment. That's important to know, because if you scan the literature, you will see just about everything done by EBM. So there's nothing limiting. People have also done tungsten now, and just like the Aconity machine that I will talk about when it comes to SLM, even for the EBM, there are now some experimental small systems ideal for academia that are coming up, where you don't need so much powder. It's easy to move from one material to another. There's a company called Freemelt in Sweden. They are essentially guys who were with Arcam or now GE Additive earlier, but they broke off and started that. But that's, if you're thinking of buying, it could be something to consider. You don't need so much. Freemelt. The name of the company is Freemelt. Yeah? Yes, please. Maybe because there is not so much work done on that. Yeah. Again, people should see value in it, right? I mean, I don't think it's a fact that you can't do it, right? But you raise a good point. I have also not seen so much work on aluminium. I see some in SLM because that's a colder process. So maybe people, by and large, people still prefer SLM. I don't know, but we bought our EBM first, so we worked a lot on EBM. But there are far more laser powder bed fusion installations worldwide, many more than EBM. But coming back to your question, I don't believe there is a limitation, but I'm not so sure. Yeah. The electron beam in this case, yeah. No, it won't. It's essentially because of because the heat input is localized. Yeah, and that's true for a laser as well. The heat input is very localized. So maybe I have that cartoon when I talk about SLM. So if you're talking about let's say location, it jumps 1, 15, 30, 45, then comes back and do 2, 16, 31. So they are not doing adjacent to each other, right? So if you do it at one spot, the rest of it kind of serves as a heat sink, right, in the vicinity of that. So, and in any case, you don't care if it heats, right? But it doesn't so much. But in this case, the bed itself is pretty hot. Yeah, it stays hot. It's just the strategy of how you melt, and that, how do I say it? I don't want to jump the gun, but how you melt then will determine whether you are going to get a columnar structure or an equiax structure. Yeah, so I don't want to get into that kind of depth, right? But that is what it will affect. Yeah, and that is why you need to play around with what is called the scan strategy. It's not as though that's the only way it will do. You can do it in a completely different way. You can do all tracks next to each other, no problem. It can be done, but it's your homework as a designer to decide how to do this, right? Yeah. Some added benefits of EBM as opposed to generic AM benefits. Yeah. I mentioned that you process it under vacuum and therefore good for materials that are thermally sensitive like titanium. Titanium doesn't like any amount of oxygen. The beam speeds are pretty high, can go up to 8,000 meters per second. Since this stays very hot, you rarely require any stress relieving heat treatment at the end of the build, yeah, because there are no large temperature gradients between the layers, so that works pretty well. And yeah, it's more forgiving to inherent material properties like absorptivity and stuff like that that are important in case of a laser, right? What else? Yeah, this I didn't cover. Yeah, you need the material mostly to be electrically conductive. Your roughness is huge, and I will come back to that when we talk about post-treatment. Compared to SLM or even DED, the roughness is much higher in case of EBM. This not strictly a limitation, but it is because it is done in vacuum. There is a limitation to what chamber size exists. So when I prepared this slide, this was just about the biggest EBM that was available, right? And then also, as I mentioned, not so many manufacturers of EBM equipment worldwide, unlike the laser part, right? So I knew of Arcam, I know of Freemelt, and both of those are in Sweden right now. I don't really want to go through all this. I think I could stop and we could chat a little bit, because all this you will see anywhere in literature. There are many things you can do with EBM. All difficult kind of materials. We were talking about implants. You can do different kinds of implants, very complex titanium aluminide blades, and there are several parts here as well where GIAN Aerospace is looking at deploying AM, but yeah. Yeah, there are many. I just don't want to go through that unless you have a specific question. Come back, start here again. No, people use all sorts of stuff. Yeah, and if you ask why, you will not get a good answer. Yeah, because that depends really on how much they have investigated the effect of scan strategy. Yeah, so either they may have an answer, or they just may not. Yeah, it depends. Yeah, it depends. Yeah. But for our part, we have seen that it makes a columnar structure fully equiax depending upon how we scan. Yeah, which is completely different, and therefore it will give you different mechanical properties. So, did I answer your question? Not so okay. Yeah.
One more question.
Yeah, I have all the time. No problem.
If we point at one point, does the separate different powder materials will not stick, sir? Because due to that much heat, at a certain point it will be solidified, but the heat will dissipate that much, sir. Different powder will not attach.
Like a magnet. So it will locally sinter, right? That's the purpose also. It will locally sinter based on the CAD drawing that you have sent. Yeah. So if you're building this, for example, it's a bad example, but imagine this is what you're building, right? So you will do a hatch which is like that. Yeah. First, sorry, you will do a contour that is like that, and then you will do the hatch. Yeah. So I don't know if I'm answering your question correctly. Then I go to the next layer. Let's say I've done that for this part, then the shape is a little bit different as I rise up. Then it will do a separate part where it will sinter the new layer to the already sintered layer below, right? And the rest of the powder will be loose. That's why it looks so crappy, ugly in the end, right? And then when you grid blast, everywhere where your electron beam has not traveled, that will be removed, right? And the rest will be there. Yeah, but I think it could still, the immediately adjoining powder could still stick. And maybe that's why you get very high roughness in your EBM compared to laser. So it depends on so many things, to be honest, yeah, including the quality of your powder. So, yeah, please. In situ in the sense? Yeah. In principle, everything is possible, right? But you then need, for simplicity and argument's sake, let's say you want to do something with aluminum silicon carbide composite. Yeah, are you thinking of something like that? Or in a sense, titanium aluminide, of course, single phase, but you're talking about two different powders, right? Yeah, correct. So nothing stops you from doing that, but the challenge for you is what is good to melt element A or component A, is it good enough to melt component B, right? And when you rake it, is there any segregation because of density difference and things like that? So as you get complex with, just as with material, when you get complex with chemistry also, these issues you need to resolve. At the end of the day, this damn thing is a source of high energy, that's all. Yeah? How do you deal with the rest is your problem, right? But I have identical issues. Let's say I'm making a composite. I want to add hexagonal boron nitride to my wear resistant coating. Yeah? I introduce both, right? Do I get perfect homogeneity? Perhaps not. But is that slight heterogeneity acceptable? Depends on application. So at the end of the day, you always come to it depends. Yeah. So, but it can be done. The processes themselves are not limiting. So if you have two, imagine you have two constituents with very different melting points, right? You could be looking at two very different situations, right? You could be looking at one situation where my second component, I am okay if it is not molten and I get a distributed solid second phase, right? Then there is a certain way for me to try and fix process conditions. There could be another where you don't want a particulate second phase, yeah? You want to melt both of them, right? I will use conditions that are appropriate for the higher melting constituent, correct? And assume that the lower melting will automatically melt because I have kind of fixed my parameters for higher melting. Life is not easy, boss. Yeah, you have to live with certain things. Yeah. Well, I think apart from examples, I didn't have so much to talk about. But thanks for your patience. You have survived me for more than 2 hours. Yeah, it's a good start. Thank you very much. otherwise we can wait for a couple of minutes maybe. Yeah, I'm just shutting it off. I'll put it in my bag actually. Shall we start? Yeah? I don't think guys who are punctual should be penalized by people who are coming late. Yeah, so we should start. So, we are going to continue a little bit with what we spoke about in the morning on metal additive manufacturing processes. We have titled this part 2 because I could cover only EBM in the morning. So I'll talk a little bit about laser beam powder bed, probably talk for a while on directed energy deposition and little bit on VAM. Yeah, at least the laser beam part is not so remarkably different in terms of what is involved compared to EBM. But let's start and take it a little bit slow, and then go on to feel free to stop me, of course. Right. So let's begin with laser additive manufacturing. In fact, the ASTM I think has a standard also for nomenclature, right? You will see all sorts of names for laser based additive manufacturing out there, right? But if you talk about selective laser sintering, it deals with powders, metals, and both in direct and indirect form. But as I told you in the morning, we'll continue to focus on metals, right? And specifically, I'll first begin with laser powder bed fusion. You will see all of these names referred to in literature. They mean the same thing. Yeah. Some people call it SLM. Some people call it like that, LPBF, but please understand that they mean the same thing. Yeah. Essentially, it's use of a laser beam instead of an electron beam that we saw in the morning, along with a powder bed configuration, right? So same kind of stuff. You rake, you will see the steps are the same. The dominant difference is that you use a laser beam instead of an electron beam, right? In this case, I have taken the help of one of the best engineers that I have seen in my group, Jonas Olsen, who played a big role in setting up our Aconity machine. This is an Aconity SLM. I'm not sure if there are many Aconities here in India yet, but it's a very good machine. Gives you a fair bit of freedom, as is necessary, I think, in an academic environment. So as I will show you, it allows us to do many things that normal commercial powder bed systems don't let us do. Yeah. If you look at it on a macro scale, the overall ambition is the same, right? You on a base plate, you have a bed of material, yeah, with slightly varying or wide powder size distribution, and as the laser beam moves through this bed, you get a solidified track as a consequence of the melt pool that is created by the laser beam, and the same process then repeats. You rake in another layer, the laser follows a certain contour, and you build. So in that sense, not very different from use of a electron beam, to a large extent the same, and that's what I show here. A 3D CAD drawing of the part, which you have sliced up into 2D. You send it to the machine, raking, build up, then that repeats till your build is complete essentially, right? It's good, I believe, for us to have a combination of a laser and an electron beam in our setup, because it allows us to do different things. As I mentioned to you, our electron beam is almost commercial intent, so we can't put sensors, we can't fool around with that. With this one we can do many things, which is our ambition. We spoke just a little bit about scan strategies. During lunch I introduced this slide here, yeah, just to let you know what I mean by scan strategy, right? You can follow patterns as you wish, right? And all of these give you fairly good builds actually, yeah? It eventually depends upon what you want to do, right? So all of these are okay. Some terminology that you should be aware of when you track these laser beams, the distance between the two tracks is the line offset, and you can go at it in many different ways. If you want to cool it or not cool it, or do different ways, I mean, do the contour first, all of these are essentially in your control. There is no rule that you must do a build in a certain specific manner, right? So that's important for you to realize. Materials, again, this list can be extremely long. I just wrote down some that are most frequent if you look at literature, right? But nothing stops you from doing some other material, so long as you have the appropriate powder available, right? So we've been mostly working on nickel-based alloys, now increasingly on tool steels and stainless steels, because apart from the gas turbine guys, when it comes to not EBM but the laser powder bed fusion, we find more and more interest from other companies like Alfa Laval and Uday Home, the guys who make steels from Hogan. So we have kind of spent a fair bit of time in doing things away from the nickel-based superalloys, like stainless steels and tool steels. And this schematic, as you can imagine, is exactly what we spoke about. There is a certain layer thickness which is variable. In case of a laser, it's much more easier to vary the beam spot size, yeah, using depending on what optics you have, or depending upon what fiber you have, if you are using a fiber laser, and you can again focus or defocus to further change the spot size and energy density. So yeah, gives you fair bit of freedom. Some prominent differences from my point of view between laser beam and electron beam. One is the spot size. You can go much finer in spot size with a laser. What does a finer spot size mean to you? What are the consequences of a finer spot size from an AM perspective? What does it do? Yes, of course, you're very correct. Smaller spot size means higher energy density, right? So you can concentrate your energy. But from a AM build standpoint or a build geometry standpoint, what does it mean? Precision of fusion. Yeah, I think you want to say what I want to hear. Yeah, precision of fusion is correct. Finer feature size. Yeah, you can build finer features because your spot size is smaller. Yeah, and for me that's a big advantage. Layer height 20 to 100 to 50 to 100. This reduction is essentially a consequence of the fact that you usually use slightly finer powder in SLM compared to EBM, right? And because it is finer, you can survive with the lower layer height. You can't use such a coarse powder and say I want to have a powder bed which is 20 microns. You can't do that, right? So you can do that. If you see in literature, many times you will hear a statement that laser powder bed fusion is a cold process. Yeah, by cold process you mean that the build temperature is not very high. Yeah, unlike in EBM, you are not maintaining the build at very high temperature, right? And because of the very small laser spot size, the cooling is almost instantaneous. So you don't see very high temperatures within the build. Yeah, and therefore, because of that, there is rapid heating and cooling. Yeah, because this is cold and then it gets heated up, cools down, and therefore you see a fair bit of residual stress sometimes in your coatings, unlike in EBM. So stress relieving treatment is very often necessary when you use a laser beam. One advantage of laser PBF laser based is the fact that it typically doesn't use vacuum. It used an inert environment. It can be either argon or nitrogen. We use both at different times, but yeah, you can use either. And what we spoke about feature size or dimensional accuracy, this again is an outcome of finer spot size, yeah. So what is the importance of this slide? Why is this slide important in laser PBF? Anybody? What is it trying to show? And yeah, so why is it important?
When we mix two materials at once, we can vary the temperature or the frequency.
Louder. I want everyone to hear you.
When we mix two materials together, we can easily find out the varying point and use it efficiently.
When we are mixing two materials, we can find out the varying point.
I mean absorption point, so that we don't overheat the material or the compound, so that it breaks its.
Right answer, wrong answer. Yeah, so even you have not given me the full answer. Sufficient amount of power should be provided, that is correct. So why is this important? Material density. Oh, we are going into small gullies now. This is not okay. I must first tell you, today is the only day when we have a theory class after lunch. Yeah, from tomorrow we will have lab visit or something after lunch, which is nice. Yeah, because after lunch all of us are a little bit drowsy, right? So please bear with me for one afternoon and give me a good answer. Yeah. Absorbance again. Why are you using a laser beam as an energy source, right? For that energy to be utilized, what is necessary? Correct, which is good or bad? Good, right? Correct, correct. Finally, I got the right answer after so many questions. Yeah, you are using laser beam as an energy source, and if the absorption is poor, you are losing all of that energy. Yeah, the material is not absorbing that energy, correct? So if you're doing something like aluminium, uh, you are absorbing only about less than 20% of energy. Yeah, that is not okay, because you are not utilizing all the incident laser energy. Yeah, and that's why this is important, correct? So aluminium, stainless steel, when it comes to titanium and copper, pretty hard, right? I mean, titanium is good, copper beyond a certain wavelength is pretty hard, correct? So what do you think are these red, green and blue lines? What do they mean, according to you? Huh? Correct, almost right. What does it mean?
Minimum energy, maximum absorption.
Correct. I mean, all of you are going around in circles. You are almost right, but not right. So this red line is for a normal red laser, yeah, which has a wavelength of 1080 nanometers, right? So if you are using this laser and you are trying to do something with copper and aluminum, you are in deep trouble, right? You are in deep trouble because you are wasting 80 to 90% of the energy, correct? So this laser of this wavelength doesn't work if you are doing aluminum or copper. First of all, the process is very inefficient. Secondly, if it doesn't absorb, means what? What does it do then? If it doesn't absorb, it reflects. It reflects the energy, and if it reflects, it goes back to the optics. It can damage the optics. Yeah, if you are using very high power, and if 80% of it that is reflected, it damages the optics, right? So two things happen. It's not good for the optics. It's not good for building, right? So therefore, you must use a different laser, and there's something called as blue lasers and green lasers. That's why these lines are blue and green. These lasers have a different wavelength, right? It's just so that you know, you don't have to worry about it, because mostly if you don't want to do aluminum or copper, it's not a big deal. Yeah, if you do aluminum and copper, this is something that you should be aware of. Yeah. Today I was talking to somebody in the morning. I don't know if it was one of you, but suppose you have this laser, yeah, and forget about AM for a while. Yeah, let's talk about something simple, cladding. You just want to do one layer or two layer. If you have this laser and you have to deal with aluminum and copper, what will you do? Coating? Like? Very good. Exactly correct. What can it be? Zirconium. I mean, perhaps you can use, but why do you want to make life so complicated? Yeah. Copper. You are struggling with copper. Yeah. You can't put copper on that. No. You want SS304. No. You can use simple graphite spray that you get in any shop. No. Yeah. So it suddenly absorbs a lot. We used to do that quite a bit. Yeah. So if you are dealing with something like this, which is very reflective, then you can use something to absorb, right? Then the other questions can come, but that's for you as a designer to address, whether that carbon can contaminate, or will it add value, will it form some carbides and actually benefit also apart from increasing absorption. All those are other issues, but either you change the laser or you use something to improve absorbance. Yeah, okay. All right, yeah. This is our Econity machine, as I mentioned, at the University West in our group. And we are trying to do these following things with the laser. I thought in case of a laser beam I should talk about that, because otherwise process wise laser or electron beam almost the same. But some of the things we are trying to do is understand the process, try and get almost completely defect free components, right? Sometimes it's almost impossible to get defect free, but at least minimize defects, right? We are heavily focused also on process monitoring. More than monitoring, our interest is in exploring whether monitoring the process will allow us to do some kind of feedback control, yeah, and change the process on the fly to make it better. We do a lot of microstructure analysis. We spoke about that in the morning. Microstructure defects, and then based on that we try and correlate the microstructure to mechanical properties. Yeah. If there are defects, what happens to the mechanical properties? How are they compromised and things like that, right? Our material focus at the moment is mostly on titanium as well as nickel-based superalloys, two entirely different reasons why we do this, because of the industrial partners that we have, and I mentioned also about our interest in stainless steels at the present time. Yeah. So we have been doing many things. It is easier to change material in an Econity machine than we have experienced in an EBM, but our portfolio is certainly much wider in case of the Econity machine. We have 4 lasers in our Econity machine, which is very nice to have 4 lasers. One is a 1200 watt ring mode laser with an adjustable power distribution, and then we have 3 single mode Gaussian lasers. So we many times use all 4 of this in tandem at the same time. Yeah. And then our build volume also is not bad, 200 mm by 400 mm, which is reasonably good shape, good size. Yeah. We can change that little bit depending upon how much we want to heat it to, and we also have the kind of optics which give us a fair bit of freedom over the laser spot size, right? When we scan a laser beam over a bed, I wanted to show you, we spoke about microstructure. Most of you who are not metallurgy or materials guys may be not interested in what happens, but I am interested, right? And we like to see what a bead looks like. We call this a bead, right? So whenever we are working on something new, a new material, we try and run a laser track at different parameters to see what the bead looks like, right? So this is typically what a bead looks like. Gives you some idea about what the depth of the melt zone is, etc. We do this even more frequently in case of direct energy deposition, but it's good to, if you want to study what's happening, it's good to investigate beads like this, yeah, to ensure that your melting is complete and therefore the chances of getting defects in the build are minimized. Yeah. This is an example of all the 4 lasers working at the same time. What I showed you in the morning had an electron beam spot jumping, right? But this is 4 different lasers being used at the same time, right? So we can program the scan strategy taking into account the fact that we could have these kind of 4 lasers going at the same time on different locations in the bed, right? It allows us to do that. schematically this is what it looks like, but maybe the next slide is better. Yeah. So we have several things installed in this because our interest, as I said, was a lot on diagnostics and monitoring. So we have a camera there. We have a couple of different pyrometers that are installed there and there to understand what is happening. So these two pyrometers plus this camera give us eyes into the process, right? Otherwise, oftentimes we are blind when we are doing this in a chamber, right? And we also have a fixed digital camera that allows us to look at the build platform, and we are trying to install more and more sensors and detection devices. I mean, we have been a little bit slow with this because we need to be sure that we understand the system well to before we begin to tinker with what is going on. But I think we are in a situation now where we are able to do lot many things than was possible in our RCAM EBM machine, right? Including visualization of pyrometer data like this. What else do we want to install? We want to install something that apparently allows us to detect cracks, yeah, as they form. We are still working a little bit with that. We want to install acoustic probes for non-destructive evaluation, see if that will help us. And we want to install lot more thermocouples apart from an IR camera. The nice thing is there are some hardware components there which we can remove, replace, create room for these kind of devices and things like that. So we are kind of excited about having acquired this Aconity machine, right? Let's talk a little bit about variables, right? Depending upon what literature you read, you will find various parameters being mentioned, right? I try to group them as primary variables, which are what we have largely spoken about so far. We spoke about laser spot size, we spoke about scan speed, we spoke in the morning about layer thickness. That's true in this case as well. Yeah, laser power and hatch spacing, right? Then there are exposure strategies, including the scanning strategy that can take different forms, right? Again, this is limitless. I showed you a schematic earlier. I am showing you another here, right? No, apart from perhaps these, none of these look similar to what I showed earlier. So it essentially tells you that you can move it. Laser is your tool. You can move it whichever way you want, yeah, depending upon what you think is the right strategy, right? So it gives you immense freedom to do all of that stuff. And then there are of course other machine settings. We at the moment at least we don't kind of change these so much. Part scaling, quarter blade, quarter speed. I mean, how fast do you rake? We don't think it's a super important parameter, so we don't do that so much. Of course, oxygen level is, right, because it directly influences in our opinion, any oxygen uptake in the build. Yeah, very important when you're dealing with something like titanium. Shield gas important. Yeah, so message is, it's entirely up to you, right? You have to decide what you think is important. And hopefully you make an educated guess, not a random guess, right? So you need to decide what works well. Yeah, a little bit of the same, but I think this is in the bunch of slides that you have access to. If you have tried to look at the QR code, how many of you have tried the QR code, by the way? Yeah. Works well, no issues? Yeah, everything okay? right. So you have it there, but basically what this shows is a list of parameters that I think are important, yeah, but I need not always be correct, yeah. You may think some other parameters are also interesting to look at, right, but I think these are for at least the first set of experiments that you may want to do, these may be good ones to look at, yeah. As I mentioned, you will see this being mentioned many times, indicated many times, that LPBF is a cold process, which essentially means that there is no preheating or sintering. Yeah, you don't do that like you do it in an EBM. And in most cases, the unmelted powder is just brushed off after the build. You don't need to blast it like you do in EBM, right? It's relatively less adherent. There are some other parameters here. Again, this is a selection from out of the much wider range that I showed you earlier, right? So some of these I think could be interesting for you to look at, right? Yeah, so in summary, if you want to classify what controls the quality of a build in laser PBF, I would divide them into at least three main categories. One is bunch of laser related parameters, second is scan related parameters including the scanning strategy, the spacing, the scan speed as well, and then there are a bunch of powder related parameters. We usually talk so much about layer thickness and all that, but particle shape, size, those kind of things are important as well, right? So what happens if your powder particle size is very fine? Is that good or bad, or does it have any disadvantages? If you have a very fine powder particle size, let's say 5 to 15 microns, huh? It will easily melt. Is that good or bad? Bad, good, bad. Yeah, if you have very fine particle size. If it easily melts, it's good. Can it vaporize? If you are talking about metals, and if it's very fine, it could vaporize as well. That is surely bad. Yeah. So, but yeah, you should be careful about what kind of powders you use. You can to some extent control powder bed temperature. Some people choose to heat the powder feeder to make sure that there is no agglomeration or clogging or things like that. Sometimes that is important, but yeah, this would be a summary of what you would want to look at, right? Also, I thought I will show you this cartoon, right? This is a pre-placed powder example where you have an incident laser beam, and then these are the kind of single tracks that you overlap as you move from track to the other, right? So this is what you're getting in an effort to completely sinter the part from one layer to another, right? Any questions so far? Can we move on? Yeah, anybody? No? I showed you that little picture with 4 lasers, yeah, that we have, but the Aconity machine, from what we have heard, can go up to 12 lasers. It can have up to 12 lasers. What's the advantage of having multiple lasers? It makes it possible to build. Is there a comment? Someone said something? No? Yeah. It makes it possible to build a larger system if you have multiple lasers, right? By separating the lasers so that you can cover large areas. So although our laser may have a certain build area, I don't think it is very restrictive. You can of course make it bigger if you are going to have more lasers, right? And the interest in doing that is so that it allows you to build larger parts which are not constrained by the volume, right? Otherwise, at the moment, the general perception is that if you use PBF, you can only do smaller parts, right? But using something like this opens up possibilities to make it much larger, especially since you are not using this in vacuum. You are using it in a controlled inert gas environment. So that is one of the drivers why you may want to do this. In principle, why not? If you can control what each of these 12 lasers is doing at different parts on the bed, it's a good point. Why can you not be doing different components at different places, right? So, yeah. So I think it opens up many opportunities, even if you are doing just one component, which is not so big. But if you have 12 lasers doing, you can increase productivity. You can build many more parts at the same time. So, that will be sure. I mean, especially if you are building different components which have obviously different constraints. Yeah. Well, that you will always need to do when you start to do a new component. You will have to in some ways optimize. So if you're building 12 different parts, I imagine that you will have to optimize 12 different things. Yeah. So, but that's okay. That is usually one time if you're producing in large numbers. So that's not so bad. Yeah. And then many times you have to worry about, if you're using multiple layers, you have to worry about overlap, because it takes me back to the time when we were using a laser not for additive manufacturing but for hardening or heat treatment, right? When you have this kind of overlap, then the region which is hardened gets softened when you overlap, correct? So you need to be a little bit careful about ensuring what happens in this overlap and whether you are influencing in some way the densification that is happening, or you are causing more problems in that area of or region of overlap. So you need, yeah. Very interesting question. Fantastic. Yeah. It's a good question. I've not seen anyone do that, but I think there is a problem with that. But what is the problem? I mean, I was immediately surprised by your question, and I thought it's a good idea, but it's not such a good idea. Tell me why not? In a laser PBF system. But I think his answer is 100% correct. You cannot rake a bed with different materials in different places, right? So your raking is a problem, right? It's not so much about 2 powder feeders. You can always have 4 powder feeders. That's not a problem. But when you rake a bed, yeah, you cannot then segregate islands of different materials. So very good. I will buy you coffee today. Yeah. Well done. Yeah, but very good point. Yeah, post-build operations, same as what we saw in EBM. Yeah, I don't really call it post-build operation. It is just to get the part out from the build, right? And all of this I will postpone until another time. Stress relief This is much more important in laser rather than in EBM. Why? This is a revision question. Why is it more important in laser beam than in EBM? Stress relief. Residual stresses are greater in case of because of temperature variations, right? Heating and cooling is a lot more. So yeah. But yeah, for the time being, let's just say that this is a very important part, right? And we'll come back to that later. Applications many, at least in Sweden and in many parts of Europe, this is a big application, medical implants. We spoke a little bit about that. The advantage derives from the fact that you can personalize implants, yeah, and print them at site, print them pretty quick, yeah. So it can be printed in no time. I've seen or heard people print this an hour or two before an operation. So everything is pretty well set. Very impressive if you are able to do this, right? So they do a scan. From that they determine what kind, what size, etc. They extract the image from the scan. They slice it up based on the scan, and then it goes for printing. Right? Very nice. So if I get operated sometime, I would like to use this. So excellent. Yeah, aerospace, of course. A big driver. This is, you must have seen this picture the maximum number of times, right? Everywhere. Yeah, correct. Yeah, where this reduced the number of components by a zillion times or something. So they talk about it all the time. But yeah, so once again takes me back to what I said in the morning. AM is not a solution to everything, but it is also not a hype. Yeah, so there are some very real parts that are out there, and that is only increasing with time. We did a project for Alfa Laval where we are building the entire reactor in AM, and that's why they are coming back to us now with a bigger project. So yeah, all of these are pretty real applications today. Yeah, I suppose this is on your QR code as well. I won't go much into that, but there are many parts, right? Each of them needs to be dealt with in a specific, special way. That's all you must know. But there are many things you can do, yeah, provided you are convinced that AM is the right way to do it, yeah. So, summary now, couple of slides maybe. Advantages, near net shape, you can make very intricate cooling channels, becomes very relevant for turbine blades in particular, where cooling is a big problem. You can get feature size or resolution details which are much better than what you can get in with an electron beam. These are lousy advantages which are kind of general, but yeah, look at that, right? It interests many industries, so it should interest you as well. Yeah, limitations, relatively low production rates. This is expensive. I mean, that's what we are talking about in the morning, that it's not always sustainable, right? Even though it may seem like a smart idea, you don't want to do this on everything that you see in life, right? There are certain components which are ideal to be considered for AM, and so there are some others which are not. So you should be careful about that. This is what I was saying, right? You can build 12 components on a bed, but every material, every component needs to have a separate set of process parameters which needs to be individually developed, right? Not easy to extrapolate, not advisable to extrapolate also, yeah? Whether you like it or not, sometimes you get a little bit of porosity with some materials like CM247. They are prone to lack of fusion and cracking defects. So that's something you need to either address or know how to deal with through appropriate post-processing, right? And we will come back to that another time. But some defects which are in the interior of the component can be solved by hipping. How many of you know hipping? Who has heard of hipping? You have heard of hipping? Who else? No? But we talk about it on Wednesday. Hipping is hot isostatic pressing, yeah? And then that can take care of several of these shortcomings, but only if they are open to surface, yeah? Sorry, post lunch. Only if they are not open to surface. If they are open to surface, you can't do anything with hip also, yeah? So they have to be at the interior. Yeah, we spoke about residual stresses, not a problem. There are standard stress relief treatments that I shouldn't use the word standard, but there are stress relief treatments that are available. Distortion is trickier, if there is, you should ensure that there is no distortion. Poor surface finish, but that is relative, right? Poor surface finish compared to what? Yeah. So I would say this gives you a better surface finish compared to EBM, yeah. But most of the guys who are used to looking at conventional machining, for example, and they say, oh, you are saying laser powder bed fusion is near net shape, yeah, and then they get very disappointed by the surface, right? So it's not as good as what you get from machining, but it's not that bad when you compare it with EBM. Just couple of other points I want to make, that this needs to be done properly. It can be a turbulent process. Turbulent probably is too strong a word. I should qualify that. By turbulent, I mean that when you scan a laser beam, right, and melt the pre-placed bed of powder, right, there can be some splashing, yeah, when the powder bed melts, right. There can be some splashing, there can be some vortex formation as you see there, and if this kind of splashing occurs, that can cause problems, right. So you must be careful that you optimize everything that you do so that this kind of splashing or spattering doesn't happen. Why is splashing a problem, you think? Atom. Powder. Then you will say particle next. Yeah.
Not every grain structure is in proper shape. Now, if there is a one grain structure missing, there is a vacancy. It creates a defect or an air bubble. So it can crack the material or it can defect it. So you minimize the.
I will take away the coffee. I am telling you. If you answer, if you have used all words, no? Grain, powder, particle, then atom also you used, no? That's not okay. You must use, as an engineer, you must use the right terminology. Very important, right? But let's try once more. What's the problem if there is splashing?
Thickness.
What happens to thickness? It reduces thickness. Oh, because one particle has gone off and sat there. Yeah, is that what you're saying? That's why it reduces thickness. Correct. Now coffee has migrated there now. Just joking. I buy both of you coffee. Yeah. So why does homogeneity go? I am making it harder. Why should it spoil homogeneity? Correct. So it has been thrown away and it has formed a little spatter somewhere else. So one particle has gone. So what does it do? Yeah, I mean, we are almost getting there. Imagine that you are correct. All right, granted. Yeah, the real problem comes when when the next raking is happening, right? Yeah, and then if you have a particle which has spattered and which is sitting like that, yeah, imagine that there is a spatter which is not necessarily a single particle now, because it has come from the molten pool, and there is a spatter and which has come and it is sitting like that. That is what causes the problem, right? And then you have raked, you have formed a bed which kind of forms around this spatter, right? And then you come back and do laser beam, everything else gets solidified, and then you get this kind of defect. But very good. These are good answers to hear after lunch especially. Well done. Yeah. So these are the problems when you get spatter, and that's what you want to avoid, correct? Yeah, there are different things showing essentially what happens because of spatter, no problem. So summary LPBF pretty strong, very popular. I think most popular among the powder bed techniques. More and more people coming up with more innovative equipment, right? And that's why you will see so many sources of laser powder bed fusion equipment compared to electron beam. Many, right? Lots of business cases to show that one can really take advantage of the various things that it can offer, including making functionally graded materials. And this is a little bit challenging, but we can do that. Yeah. Yeah. Huh?
Mostly the welding and also the machine work.
Correct.
We are not involving any hand work. So how can we control this flashing? Flashing. How can we control?
Flashing. Yeah. You tell.
I don't know, by decreasing the speed.
Supply sufficient amount of laser power to control the laser spot cells.
You should not over melt. The splashing happens if you have if you have melted it a lot, if your gas flow is too much. So there are certain things that will cause splashing or spatter, right? You should take care of those kind of things. Yeah, you don't control that by controlling raking. It's happening before that. Yeah, so the control has to be on melting. Yeah, heat input. Yeah, stuff like that. You have some questions? No? Otherwise, you should tell us all, then it will be fun. Yeah, so tea? Very good. You're getting a tea break. But this is not yours. I'll give you separate. Yeah, okay. So we go out, is it?
Yes, sir.
Yeah, come. Tea break, guys, quickly. You gave me tea at just the right time. I was beginning to fall asleep a little bit. So I'm not used to talking for so long. No, it's rare for me. But let's switch tracks a little bit. We've spoken about powder bed fusion so far. I'm going to stick with laser for the time being, but talk about directed energy deposition. I like directed energy deposition because I was doing DED from before powder bed fusion and things like that when I was in Hyderabad at ARCI. I've taken help of my colleague Jorg, used some of his slides from before to talk about this. I also mention Jorg because we have a very smart student from NIT Warangal now, for whom me, Jorg and another colleague of ours, Joel, we three are the supervisors for Hemchandra, who was here not so long ago. So we'll talk a short while about directed energy deposition. Again, all these things, AM has suddenly become fashionable, but these techniques have been around for a long time, and therefore they have been known by many different names. I remember 1990 something when I was at DMRL, we had yeah, we had a equipment for lens which was called laser engineered net shaping, or it's also known as LMD, directed metal deposition. I now know the trick to exit from here. Oh, but I may not have internet access, so maybe I can't show you a video. Can we have internet access on this? No, right? Can I? Sorry about that. I should have done this during the tea break, but I didn't expect. Otherwise, we skip. Let me check. No, I don't have the connector. Oh, that would have been useful. Yeah, let's just try once. If not, we'll forget about this. Up to 9. Oops. No. You had put 9 also, right? All smaller.
Yes, sir. At the rate 214.
When did you do NAT FOE? Oh, nice. Yeah, sure. Let's try if this works, otherwise we can forget. So this is a little video which I like, and that's why I thought I would show you. This relates to the lens, which is essentially the same. I mean, it hasn't changed so much from what is today known as directed energy deposition, but very nice. It gives you a whole lot of freedom, almost like thermal spray, where you can use any powder. There are not so many issues, and it can build pretty fast. Yeah, earlier you used to use something like this for cladding, yeah, as a surface modification technique, but now you can use it for not just functional surfaces, but doing AM, especially for repairing components, and in this variety you use it as a coating, yeah, when there is wear and things like that, right? So especially today, you have all sorts of ways to manipulate relatively the laser head and the job, right? So again, the basic principle is the same, that for any given material that you want to deposit, you need to optimize how it melts, etc., for the kind of laser that you have. But it's nice to see this happening, right? So you can do very thin wall features because of the spot size that is available. And today it's a very popular method to do blade tip repair especially, right? All kinds of turbine blades, which as you know are very expensive. Each blade costs almost, right? So people use this a lot for very localized repair with small feature size and at fairly high deposition rates. And then you have a very high choice of materials to pick from. Almost the same spectrum that we saw in the morning for EBM, all kinds of nickel-based superalloys, titanium alloys, and things like that, right? I think I need not go more into that. So the nice thing in my perspective about directed energy deposition with either powder or wire is reflected in this cartoon. You can use a wire instead of a powder, right? The point always is that you want to introduce the material with which you want to build into what is called the interaction zone. Interaction zone is where the laser beam interacts with the top surface, right? And that's what you want to accomplish. As you can imagine, there are many variants of that, correct? Let's forget about wire, although it's very important and I may come back to that. But you could feed the material in powder form in many different ways. In old times, when the nozzle design was not so fancy or not so evolved, this is how we fed the powder stream, yeah, at an angle into the interaction zone. Now we can do many different things. You have multiple feeders, yeah, which are aligned so that there is radial symmetry that is maintained, yeah. You don't want it skewed on one side, or better still, you now have coaxial powder delivery system, right, which goes right through the nozzle, center of the nozzle, where the laser beam also comes from, yeah. So that is clearly the preferred orientation. So just as a recap, you can use coaxial powder, you can use coaxial wire, or you can of course use off axis, either powder or wire. And all of them are pretty successful in accomplishing what we want to do, either few layers in the form of a cladding or a coating, or multiple layers to build an AM part, yeah, of the kind that you desire. So here is an up close arrangement. What you need to always ensure, regardless of the manner in which you introduce the powder, is this, that it is fed into the interaction zone, right? And if you do that well, whatever people say, the general rule is the same. You will see the same kind of process variables repeated all the time. What would be the process variables here, without me saying so much? Yeah. What do you think are the process variables for a process like this? Please don't say grain size. Say particle size. I am happy with particle size. Grain size is very complicated then. Yeah. So particle size, correct. Powder feed rate, correct. What else? Rate of? It's not a variable. Yeah. Yeah. It's an output. So not a variable. Yeah. Huh? Laser power. Scan speed, correct? So same thing that I said earlier. So life is not so complicated sometimes. There's the same set of parameters. Yeah, sometimes it's complicated, but in this case, yeah, understanding what makes a difference is not complicated. Understanding it is, right? What is the effect of power on what you get? What is the effect of powder feed rate on what you get? What is the effect of particle size on what happens, right? So those are the important things. Believe it or not, people have also fed powder in different ways, right? This is leading application of powder. This is trailing application of powder. Leading means what? It leads the laser beam, and here it trails the laser beam, right? As long as you do it right, you understand what you're doing, you can make it work, right? Both of them work pretty good. But yeah, if I had the money, if I had a good coax nozzle, this is what I will do, right? Use a coax nozzle. Now you also get coax nozzle with six feeding ports, right? So if you are using 2 powders, use 1 powder in 3 feeding ports, use the second powder in 3 other feeding ports. Someone was asking me just now during the break and even earlier about making composites, having 1 powder added to the other. So doing all that kind of stuff, this is great. Powder bed is not that great. This gives you so much freedom, right? To do all those kind of innovative things, right? Even functionally graded, for example, if you have 2 powder feeders, you can control the ratio of A is to B as you do, right? You change one after the other, and then you can go from 100% A to 100% B slowly, right? So you can grade that as well. Yeah. Yeah.
Material has a different temperature.
Mm-hmm.
Different temperature.
Mm-hmm.
Now, if the laser is set to a titanium temperature point, let's say, there is no such metal in the same temperature point, and we are using it something else. It may defect, sir.
Correct.
It may defect. Then the technique is not going to be much efficient than using separate temperature and material differently.
What I said before still holds, right? If you have 2 different materials which have 2 very distinct melting temperatures, right? So that challenge you cannot get away with. It's just that your way of feeding, etc., you have more control. But other facts of life don't change. Yeah, if you have 2 different materials, you have to decide, do I want to melt both? If you want to melt both, then what parameters do I use so that the high melting and low melting both melt? Yeah, the low melting melts along with high melting but doesn't get damaged. Yeah, while I'm trying to put in more energy. Yeah, do I want the phase B to be as particulates? All those decisions you still need to make. So that doesn't change. It's just the manner in which you introduce these different elements that becomes easier, right? Rest of the challenges remain unchanged, right? And because of the freedom that it provides, we've at University West been using DED for many different things. One is to do parts like these, yeah, to demonstrate that we can build whatever our partners want. In early times where people were not confident about what we can deliver and what the technology is capable of also, we did lot of work with GIAN Aerospace to add features, right? So rest of the part was already there, made by some other process, and we added features such as these, right? So that was a low risk initial test for the technology. So we did a fair bit of that, right? And then more and more now we are looking at repair of expensive parts which otherwise need to be thrown off, right? So this is also something else that we have been doing, both using our laser route as well as using coatings that I will talk about a little bit later. I must admit I don't know what this video is, but let's try. If it's boring, we'll stop. Yeah. Isn't this the same one? What the hell? I don't want this then. Yeah, let's move on. We are back. We are back to this. Yeah. Why are we talking about green versus blue? Yeah. Because of copper. Right? One of the things that so again, same constraints apply, like you said, for melting, etc. is the same, because you are still using a laser. When it comes to doing things like copper, aluminum, you have the same issues as you had with the powder bed laser beam, yeah, because that is characteristic of a laser material interaction, right? Whether you do it in a chamber or outside, it's not going to change, right? So at the moment we are trying to decide between buying a green laser and a blue laser, because our latest project involves combining stainless steel and copper, yeah, to do a certain aerospace part, right? And we are struggling for the reasons that we have already discussed, yeah, about reflectivity and things like that. I spoke a little bit about this already, but couple of things you must know. When we talk about cladding, it's not different from laser DED. What is different is what we mean when we say cladding. Usually you're talking about a couple of mm thickness, not more than that, right? When you're talking about AM, you're talking about much bigger parts, right? When you're talking about repair, you want a very fine track if you're doing a blade tip kind of thing. When you're doing cladding, you want as wide a track as you can, right? So with the right optics, for example, if you have a point beam, with the right optics, you can convert it into a line beam, which is 10, 12, 14, 16, even up to 16 mm big, if your optics are correct. Yeah, you don't want that in repair. Yeah, you want it very specific to the feature that you want to build, right? But in cladding, etc., you want large area coverage. Most times, there can be exceptions, of course, but most of the times you want large area coverage. Yeah, to, let's say, cover an entire shaft with something which is wear resistant. So that part is very different, correct? So again, we spoke about this little bit. Main process parameters in DED, laser beam spot size. You can focus, defocus, use the right optics, convert into a line or whatever you want. Process speed, power, feed rate, laser beam part width. By this I mean overlap. We spoke about overlap as well. And yeah, so these are again same as what we saw before. Again, many examples of this. This is the one that I like the most, because this was one of the first things similar to this that we did, but this particular one is an example from our collaborator at Fraunhofer. Yeah, you can always see that the laser beam, if the powder is fed correctly, it's a very stable deposition process. Yeah, extremely stable. You don't see any variation. There are no raking issues, but you need to feed it well, right, the powder. And most of the feeding issues are resolved if you have the coax nozzle, right? Coax nozzle is something which is great. Quick difference between DED and PBF. As you can imagine, you have much greater versatility. If you are using DED, you can use a lot more variety of materials, including mixed powders and things like that, which are slightly hard to do when you are doing powder bed. You need to have a good handling system, but that's not an issue these days. You have very sophisticated powder delivery systems that are available, right? We are today able to feed, earlier feeding finer powders used to be a challenge. Today we can feed anything from about 5 microns to 100 microns, yeah, with great reliability. So that's not a problem. Part complexity, as you can imagine, this is limited compared to both of the powder bed techniques because you're kind of doing it 2D layer by layer. As long as you do that well, this is unlimited. Here, especially when it comes to very intricate geometries like cooling holes, you can't do this. It's a little bit harder, right? Deposition rates actually much better than in laser PBF. Why? Why do you think the deposition rates are better than here? Because no raking etc. is involved, right? You don't need to rake and then locally do that, right? So your deposition rates are therefore better. You can do it much faster. You can build on just about anything, any kind of pre-existing surface. If you, assuming you have good robotic movement in a powder bed, you are in that sense constrained, yeah, because you are raking. It always needs to be a flat top surface. Of course, one can argue that this is taken care of when you do 2D slicing, right? So eventually you get what you want, but yeah, in terms of ability to deposit, you can only deposit the last layer on a flat surface. Yeah, both of these are pretty rough. Yeah, you can see the roughness here, 60 to 100 microns, but I think this roughness is a little bit misleading because you get a certain bead and that is overlapped, so it is not local roughness. It is the general undulation because of the beads that you put on. Yeah, so in that sense, little bit misleading, and you can apply this pretty thick. I mean, in regions which overlap this, but also which go way beyond what you can do here, right? In case of powder bed. So fairly strong way to accomplish many AM requirements that may present themselves, right? I want to talk a little bit about wire DD and wire based variants. Yeah? So at least at University West, we do three things at the moment. We use wire with laser. That is our longest standing research area almost, where we have used DED with laser, and then more recently we have begun to do lots of stuff with VAM. We don't do so much on hybrid, but that's something which is on the table right now because of some of the projects we deal with. The nice thing today is that just as you have coax nozzles for powder, you also have coax nozzles for wire, and we also find that we can do diagnostics much easier with wire. So there are many things special that we have done, in my opinion. We pass a current through the wire so that it provides additional thermal energy. So our wire tip is pretty hot when it touches the top layer, right? So that is a new innovation. So we do that, and then we also monitor electrical conductivity at the point where the wire tip is touching the melt pool, right? So we are able to therefore tell whether there is discontinuity or something like that is happening. That's one of the things that Hemchandra has just begun to work with, yeah, trying to correlate any excursion in that conductivity with microstructure, right? So if we see because of change in wire feed rate or gas flow, if you see that the measured conductivity is changing, we monitor that and then look at that very instant, how does the microstructure look like, or little bit later to even see if there is a lag between such an event happening and digression in microstructure. So I think that's a very interesting project that would at least form a part of Hemchandra's PhD. We are kind of excited about that. So that's with wire. Then with VAM, we think that VAM has not got the attention that it deserves, right? People have thought this as a lousy technology because it uses an arc which is very commonly available. But I think we can do lot of things with that, and most of our recent projects are gravitating around wire arc. I don't know if you do it yet, but I think this is a wonderful new area to get into. Yeah, it's fantastic. Yeah, and then there is more and more industrial interest because, yeah, because even industry is now beginning to realize this is much cheaper than everything else I have spoken about so far, right? So very high throughputs may not look very fancy on the surface, but gives good mechanical properties, especially if you're going to do some minimal machining in the end. This is great. So we've been trying to use different kinds of arcs, MIG and TIG. As I said, the biggest motivation for us is that it's a cheap source of heat for what we want to accomplish, and therefore there's a very clear business case for the industry. The deposition rates also are very handsome. As you would have seen from that wall that I showed earlier, the surfaces are kind of rough, so some kind of finishing is clearly required for most sensible applications, and but so long as you take care of that, it is pretty good. What else? I wanted to show you a couple of yeah. So for a heat source which is as cheap as an arc, this is pretty good, and it can do many things that you can see how stable that is, right? And fairly good. You can also do it localized, like you see it there. It can allow you quite a few degrees of freedom. See, build locally whatever features you want to build, right? So depending upon what your end application is, you can accomplish many things with VAM. Much of the stuff that we have been doing so far is demonstrating to our partners what level of complexity is realizable using such a cheap technique even. So that's quite nice. There are many processes available. I just wanted to put this down, but not everybody has that choice. For example, we don't have access to all of these, but you must know what tool you're going to use. But having done that, you have a choice to make there. That is something that you must know, right? One other thing I wanted to point out, if you look at the process window for doing VAM, you have different regimes where some short circuiting takes place of the wire feedstock, and then you see some pulsing, and then somewhere the wire comes out as wire spray, you know. So you need to be clear about where you want to operate your VAM process, right? I mean, some of these work pretty well actually. So, but we oftentimes try to be somewhere here, right? So this is a short circuit transfer, right? As you can imagine, it is short circuiting that thing pretty good. Yeah, yeah. It's a very high speed camera. This is something from one of our collaborators. It's not our work, but it clearly shows the different regimes in which material transfer happens. Yeah, yeah. So this is like a short circuit, right? When it touches, then it gets transferred. In this particular case, quite nice to see that happen. This is a droplet transfer. This is a completely different regime in that chart. Yeah, so you see, let that droplet form, and then it kind of drops on the substrate to be coated. So yeah. So I found that very fascinating. So I thought I must share that with you. It clearly shows how the deposition regime varies at different times. So, and many things affect this. As you can imagine, the rate at which you're feeding, even the carrier gas that you have, yeah, you don't want it to disturb what is happening there, right? So quite nice. This is like a spray transfer, as you will see now. I hope it works. So this is a completely different regime where it's coming like a spray, right? It just goes to show that if you know how you're doing it, there is great control possible, right? While you're using the wire arc. This is the last one then. So it's not coming as continuously as the other one, so that's why it's a little bit, they call it pulsed. But you are able to do all of these things, right? And at the end of the day, it's all about knowing what is going on, right? I remember one of the first components that I did when I was in DMRL for one of the missile parts. I proposed something and director said, "Why are you doing this? You will also get fired and I will also get fired." No? But it was one of the cheapest oxyacetylene flame torches, right? But the point is, you must understand what the application demands are and what you are capable to do. So I think this could be a cheap process, but it is very, very powerful, right? If you know what is going on. One of the things related to WAM with which we are having a lot of fun right now is to decide what the shielding gas mixture is. So now we are in a situation where we can tell the gas supplier that we want a specific mixture of gas to be bottled and given to us, because we see a lot of difference based on this chemistry on how the characteristics of the build layer are, right? So this is our current focus, to look at the role of gas chemistry on. So this is something new. You don't see so much of this in powder bed fusion or DED, but we are finding this to make a big difference, and that's something that we are working on. This is just a cartoon showing how, depending upon the gas, but with everything else the same, the beads vary to a large extent, right? And that's not an exaggeration. So that's the reason we are trying to strike a compromise between something like this and something like this by kind of evaluating various other regimes in between, right? No surprise, we spoke about scan pattern there. Even here it makes a difference. So the path sequence protocol is important, just so that you know that, right? I mean, you should be aware of it, that's all. Yeah, I don't want to spend so much time on it, but it really depends, depending upon the geometry of the component that you are building, you must come up with a good way to optimize the path so that there is no hot spots or thermal runaway in your part, right? Yeah, we've been trying many different things in terms of path planning, but eventually one needs to do an exercise of this sort, especially if the part is very complex. Yeah, but it's doable. It's not complicated. It's just for you to be aware that something like this is important to consider, right? I'll kind of stop here. I'm on time, but I'm happy to stay as long as you want if there are questions, right? And then tomorrow we talk a little bit about feedstock, I think. And then, do we talk about, yeah, I don't remember the schedule, but post-processing, yeah, or maybe feedstock in the, let me quickly pull that up so that you know what's going on tomorrow. Are there any questions? Oh, we have two. So we talk about feedstock in the morning, and then post-treatment either in the afternoon or we switch. And I do this also in the morning. But these are the two things we will deal with. Yeah, feedstock for metal AM and post-treatment of AM. All right. Questions? Tired, everyone? Long day? No? But if you have no questions, I am done. Yes, please. I think there's some confusion here.
I'm asking about laser wire direct energy deposition.
Laser wire.
Yes.
Okay.
It's a laser powder
Yeah.
direct energy deposition.
Okay.
Which can more sustainable.
For me, both are the same, almost. Yeah. Unless we dive into sustainability from a processing standpoint for powder production and wire production. But we are very happy with wire. Yeah, wire is much better. At least in our experience, the throughput with wire is superior. I may be a little bit biased though, because we have worked much longer with wire. So we understand it inside out. We know how to do this feedback control with wire. We don't know that so well with powder. Yeah, because with wire we know the rules. Yeah, correct. So we understand wire much better. At the end of the day, I think it's all about understanding the process. I remember 1989, seems like very old to you guys, but when I first started working with plasma spray, thermal spray and stuff like that, companies would come and say, this is our equipment. If you buy our powder, here is a spray sheet, you plug in those numbers, then you will get good coatings. But if you don't buy our powder, you are in deep trouble, right? And everyone believed that at that time, right? Everyone believed that, oh, if I don't buy this guy's powder, my coatings will be horrible. Because at that time we didn't know, we didn't understand the process. Even today, exactly same situation, that thermal spray one, right? So today if you buy an RCAM machine, RCAM also makes powders or has someone make powders and it markets, saying that if you buy this powder only, you will get good yields, right? Otherwise, so, yeah, correct. Yeah, exactly. That's another issue. But once you start, today we can take any powder, China, good, bad, ugly, whatever, and do coatings, no problem, because we fully understand what's happening. In due course, we will fully understand what's happening in AM also, and then we'll be able to use whatever. So, but these are normal teething problems with new technology. We shouldn't say new at this point because it's been around for a while, but yeah, I think we are still kind of scared about what will happen if we use something like this. But you shouldn't be scared, is my message. It works. All right.
selected date for today. And tomorrow the sessions will start at 9:30. So all of you be positively, be here by 9:30, at least 10 minutes before.
Do we start at 9:30 because maybe the program says something else, or?
At 10 o'clock, yeah.
But no, we can start at 9:30 actually, no problem.
9:30.
Shall we start at 9:30 so that we finish early also? So 9:30 then.
And
So
then probably the sessions will swap depending on the convenience of Professor Joshi. And another small thing is for dinner you have to be on your own. That's the course funding guidelines, so we can't help it. So please try to understand the situation. And those who are staying in hostels, they can approach either hostels and inform them for providing dinner. You can take the help of some of our students. They are there to guide you. And those who are staying in the guest house, they can also inform the guest house caretaker, and he'll, on chargeable basis, he'll arrange. Or otherwise, you are free to move outside. It's up to you. Okay? So let us meet again tomorrow at 9:30. Thank you.